What if tomorrow you woke up and couldn't breathe the air outside your window? Not because of pollution or smoke, but because the very atmosphere that sustained human civilization for millennia simply stopped working for us. Right now, as you listen to these words, you're participating in an extraordinary cosmic accident, existing on the only known planet where creatures like us can survive without life support systems. This isn't science fiction. This is a genuine scientific question that keeps researchers awake at night. Will our home planet eventually become uninhabitable for human beings? And the answer isn't as straightforward as you might expect. Consider this startling reality. You're currently living through the most stable climate period in Earth's entire 4.5 billion year existence. Yet even during this golden age of habitability, our planet has experienced massive ice sheets covering continents, volcanic eruptions that blocked sunlight for years, and ocean chemistry changes that eliminated entire marine ecosystems. The difference today is that for the first time in planetary history, one species, hers, has gained the power to influence these global systems. But let's step back from the human element for a moment and examine what makes our world livable in the first place. Understanding these mechanisms reveals just how precarious our situation really is. Earth occupies what astronomers call the habitable zone, moles and a narrow band around our star, where temperatures allow liquid water to exist. This cosmic sweet spot isn't just about distance from the sun, though that's crucial. Move our planet just 5% closer to our star, and runaway greenhouse effects would eventually boil away our oceans, leaving us with a hellish Venus-like atmosphere. Shift us 5% farther out, and global ice coverage would reflect so much sunlight that we'd spiral into a permanent frozen state. But orbital position is only the beginning of our fortunate circumstances. The air you're breathing right now represents billions of years of atmospheric evolution. Early Earth's atmosphere was completely toxic to life forms like us, dominated by methane, ammonia, and other compounds that would kill humans in minutes. The oxygen that sustains us today didn't exist until ancient bacteria began photosynthesis, gradually transforming our planet's chemistry over geological timescales. Even now, our atmospheric composition exists within razor-thin margins. That life-giving oxygen makes up roughly 21% of our air. Increase that to 25%, and forest fires would rage uncontrollably across continents, making plant life nearly impossible. Decrease it to 15%, and human consciousness would fade as our brains struggled with oxygen deprivation. The nitrogen that comprises 78% of our atmosphere isn't just fill a mine, it provides the pressure needed to keep water liquid at Earth's surface and prevents oxygen from becoming toxic at current concentrations. This atmospheric pressure serves another vital function most people never consider. Without it, the water in your bloodstream would literally boil at normal body temperature. Your cells would rupture, your tissues would expand catastrophically, and death would occur within minutes. This is why astronauts require pressurized suits in space, so not just for oxygen, but for the pressure that keeps human biology functional. Gravity plays the unseen hero in maintaining these conditions. Our planet's mass creates precisely the right gravitational pull to retain our atmosphere, while allowing enough atmospheric escape to prevent toxic buildup. Too little gravity, and our air would gradually leak into space like it did on Mars. Too much gravity, and we'd retain every gas ever released, creating a crushing, poisonous atmosphere like Venus. Then there's our magnetic field, an invisible shield generated by Earth's liquid iron core that deflects deadly solar radiation and cosmic particles. Without this protection, solar winds would gradually strip away our atmosphere while bombarding the surface with radiation levels that would make complex life impossible. Mars lost its magnetic field billions of years ago, and you can see the result: a thin, cold atmosphere incapable of supporting liquid water on its surface. Our moon contributes to habitability in ways that seem almost designed for life. Its gravitational influence stabilizes Earth's axial tilt, preventing wild climate swings that would occur if our planet wobbled chaotically. The tidal forces it creates help stir early oceans, potentially jump-starting the chemical processes that led to life. Even today, tidal mixing helps regulate ocean temperatures and nutrient distribution. Water itself presents another remarkable circumstance. Unlike most substances, water expands when it freezes, causing ice to float rather than sink. This seemingly simple property prevents bodies of water from freezing solid from bottom to top, preserving aquatic ecosystems during ice ages and maintaining the water cycle that distributes heat around our planet. The carbon cycle represents perhaps the most elegant of Earth's regulatory systems. Plants absorb carbon dioxide for growth, while geological processes bury carbon in sediments and rocks. Volcanic activity releases stored carbon back to the atmosphere. Ocean chemistry buffers atmospheric changes. This complex dance has kept global temperatures within bounds compatible with life for hundreds of millions of years. Despite massive variations in solar output, volcanic activity and biological changes. Geological processes contribute their own stabilizing influences. Plate tectonics recycles carbon through rock formation and volcanic emissions. Mountain building affects weather patterns and creates diverse climatic zones. Even the composition of our planet's crust provides the mineral nutrients essential for biological processes. Consider how many variables had to align perfectly for you to exist here. Now, breathing freely while contemplating these questions. The right star type with stable energy output. The right planetary size and composition. The right atmospheric evolution. The right magnetic field strength. The right orbital characteristics. The right moon size and distance. The right geological activity levels. Yet despite these seemingly stable conditions, Earth's climate has never been truly static. Ice ages have repeatedly transformed the landscape. Massive volcanic eruptions have altered atmospheric chemistry for decades. Asteroid impacts have triggered mass extinctions. Ocean currents have shifted, changing regional climates dramatically. Supervolcanic eruptions have blocked sunlight and cooled global temperatures for years at a time. What makes our current era unique isn't climate change itself. This always occurred. What's unprecedented is the speed of change and its cause. For the first time in planetary history, a single species has gained the ability to alter global atmospheric chemistry, ocean pH, and surface temperatures within decades, rather than millennia. This brings us to the central question. Given how many precise conditions are required for human habitability, and given our growing influence over these systems, what could actually make Earth uninhabitable for us? The answers might surprise you because they're not what most people expect. Here's something that might keep you up tonight. The protective magnetic shield surrounding our planet isn't permanent. Scientists have discovered that Earth's magnetic field has completely flipped its polarity hundreds of times throughout history, and it's currently weakening at an alarming rate. During these magnetic reversals, which can take several thousand years to complete, our planet becomes temporarily vulnerable to deadly cosmic radiation and solar particles that could strip away portions of our atmosphere. The last complete reversal happened 780,000 years ago, and geological evidence suggests we're overdue for another one. While life has survived previous magnetic field collapses, modern civilization base, with its dependence on electronic systems and global communication networks, would face unprecedented challenges during such an event. Satellite navigation would fail, power grids would experience massive disruptions, and cancer rates would skyrocket from increased radiation exposure. Water presents another deceptively complex challenge to Earth's continued habitability. While our planet contains roughly 1.4 billion cubic kilometers of water, only 2.5% of that total is fresh water, suitable for human consumption and agriculture. Most fresh water remains locked in polar ice caps and glaciers, leaving less than 1% readily accessible for the 8 billion people currently alive. This precious resource exists in a constant state of flux. Glacial melt doesn't just threaten coastal cities with rising sea levels and sea levels, it also disrupts the global circulation patterns that distribute heat and moisture around the planet. The massive ice sheets of Greenland and Antarctica act like giant refrigeration units, reflecting solar energy back into space and maintaining cooler global temperatures. As these white surfaces shrink, darker ocean water absorbs more heat, accelerating warming in a feedback loop that becomes increasingly difficult to reverse. Underground aquifers that took millennia to fill are being drained in decades. The Ogallala Aquifer beneath America's Great Plains, which supports 30% of the nation's irrigation needs, has dropped by more than 100 feet in some areas since the 1950s. Similar depletion patterns are occurring worldwide, from India's Punjab region to Australia's Great Artesian Basin. When these ancient water reserves disappear, the agricultural regions they support cannot easily transition to alternative water sources. Rivers and lakes face their own mounting pressures. The Colorado River, which provides water to 40 million people across 7 states, no longer reaches the ocean due to overuse and persistent drought. Lake Mead and Lake Powell, crucial reservoirs in this system, have fallen to historic lows, threatening hydroelectric power generation and municipal water supplies. Similar scenarios are playing out globally, from the shrinking Aral Sea to the stressed Nile River system. But Earth's biological networks might represent the most critical Molma-Fadal-Samnul's component of planetary habitability. These interconnected webs of life don't just provide resources, they actively regulate atmospheric composition, soil chemistry, and climate stability. When functioning properly, biological systems create powerful feedback mechanisms that help maintain conditions suitable for complex life. Forests demonstrate this regulatory power on a massive scale. The Amazon rainforest generates approximately half of its own rainfall through transpiration to trees, releasing water vapor that forms clouds and falls as precipitation deeper in the forest. This self-sustaining moisture cycle supports not just the rainforest itself, but influences weather patterns across South America and beyond. Researchers have identified a critical threshold. If deforestation reduces the Amazon below 75% of its original size, this moisture recycling system could collapse entirely, transforming the remaining forest into savanna within decades. Ocean ecosystems provide equally vital services. Phytoplankton microscopic marine plants produce roughly 50% of the oxygen in our atmosphere, while absorbing enormous quantities of carbon dioxide. These tiny organisms form the foundation of marine food webs, supporting everything from small fish to great whales. Yet phytoplankton populations are declining as ocean temperatures rise and water chemistry becomes more acidic from absorbing excess atmospheric carbon dioxide. Coral reefs exemplify the intricate connections between biological diversity and human survival. Despite covering less than 1% of ocean area, coral reefs support approximately 25% of all marine species. They provide coastal protection from storms, support fisheries that feed hundreds of millions of people, and generate billions of dollars in tourism revenue. Rising water temperatures have already triggered massive coral bleaching events, killing reef systems that took thousands of years to develop. Soil represents another underappreciated life support system. Healthy topsoil teems with bacteria, fungi, insects, and other organisms that break down organic matter, cycle nutrients, and create the conditions necessary for plant growth. This biological activity takes centuries to develop naturally, yet industrial agriculture and urban development can destroy productive soil in mere decades. The United Nations estimates that 1/3 of the world's arable land has been lost to erosion and degradation over the past 40 years. Pollinating insects provide a direct link between biological diversity and human food security. Bees, butterflies, beetles, and other pollinators enable reproduction in roughly 75% of crop species that humans depend on for nutrition. Colony collapse disorder and pollinator population declines threaten not just honey production, but the fruits, nuts, and vegetables that provide essential nutrients for human health. The planetary boundaries framework reveals how these interconnected systems create stability through their relationships with each other. 9 critical Earth system processes here including climate stability, biodiversity integrity, biogeochemical cycles, and land system change must remain within certain ranges to maintain the conditions that allowed human civilization to develop and flourish. Current evidence suggests humanity has already pushed several of these boundaries beyond their safe operating spaces. Atmospheric carbon dioxide levels now exceed 400 parts per million for the first time in over 3 million years. Species are disappearing at rates 100 to 1,000 times faster than natural background extinction rates. Nitrogen and phosphorus cycles have been disrupted by industrial fertilizer production and application. Yet crossing these boundaries doesn't guarantee immediate catastrophe. Earth's systems demonstrate remarkable resilience and capacity for adaptation. Some changes can be reversed if action is taken quickly enough. Others trigger cascading effects that become increasingly difficult to control as time passes. The key insight from planetary boundary research is that these systems don't operate independently. Changes in one area can trigger unexpected responses elsewhere. Arctic sea ice loss affects global weather patterns. Deforestation influences regional rainfall. Ocean acidification impacts both marine ecosystems and atmospheric chemistry. Understanding these connections helps explain why environmental changes can accelerate suddenly after appearing stable for extended periods. This interconnectedness also reveals why Earth's habitability cannot be taken for granted, despite the planet's 4.5 billion year track record of supporting life. The specific combination of conditions that allow human civilization to thrive emerged relatively recently in geological terms and depends on maintaining delicate balances across multiple Earth systems simultaneously. As we examine the mounting pressures on these life support systems, remember that we're not discussing abstract possibilities but measurable changes already underway across our planet. Our moon's influence extends far beyond the romantic tides you might watch from a beach at sunset. Those rhythmic ocean movements create one of Earth's most dynamic ecosystems, intertidal zones, where life learns some of its most important survival skills. Twice daily, these coastal margins transform from underwater worlds to exposed landscapes, forcing organisms to develop incredible adaptability. Scientists now believe these tidal pools may have served as Earth's first laboratories, where organic molecules concentrated and combined in ways that eventually sparked the chemistry of life itself. Without lunar gravitational pull, Earth's rotation would gradually slow, eventually creating days lasting several months. Half the planet would bake under continuous sunlight while the other half froze in permanent darkness. Temperature extremes would make weather patterns chaotic and unpredictable, eliminating the stable seasonal cycles that allowed agriculture to develop and civilizations to flourish. The atmosphere surrounding us represents one of the most remarkable engineering achievements in the universe, except it wasn't engineered by any intelligence we recognize. This invisible protective shell performs multiple critical functions simultaneously. It burns up tens of thousands of meteors and space debris pieces daily, preventing a constant bombardment that would make surface life impossible. It filters out deadly ultraviolet radiation while allowing beneficial wavelengths through. It distributes heat from equatorial regions toward the poles, moderating temperature extremes. But perhaps most remarkably, our atmosphere maintains its life-supporting composition through biological processes that began billions of years ago and continue today. The oxygen you're breathing right now didn't exist when Earth first formed. Early atmosphere contained virtually no free oxygen, neither would have been immediately toxic to modern humans. Ancient cyanobacteria gradually released oxygen as a waste product of photosynthesis, fundamentally transforming planetary chemistry in what scientists call the Great Oxidation Event. This transformation nearly ended life on Earth entirely. Oxygen was poisonous to most early organisms, triggering the first mass extinction as anaerobic bacteria died off worldwide. Yet this catastrophe also enabled the evolution of complex life forms that could harness oxygen's chemical energy for more sophisticated biological processes. The same gas that killed primitive life became essential for everything from insects to elephants. Current oxygen concentrations hover around 21% of total atmospheric volume minimum, a percentage that seems arbitrary but represents another critical balance point. Increase oxygen to 25%, and vegetation becomes so combustible that lightning strikes would ignite continent-spanning wildfires. Decrease it to 15%, and large animals, including humans, couldn't maintain consciousness due to oxygen deprivation. This narrow range has remained relatively stable for millions of years, maintained by the balance between photosynthetic oxygen production and biological oxygen consumption. Carbon dioxide plays an equally crucial but more complex role in planetary habitability. Despite recent concerns about greenhouse gas effects, CO2 remains essential for maintaining Earth's temperature within ranges suitable for liquid water. Without any carbon dioxide in the atmosphere, our planet's average surface temperature would drop to approximately -18 degrees Celsius, freezing most surface water and making complex life impossible. Venus demonstrates what happens when carbon dioxide levels spiral out of control. Its atmosphere contains roughly 96% CO2, creating surface pressures 90 times greater than Earth's, and temperatures exceeding 460 degrees Celsius. Nice hot enough to melt zinc. This runaway greenhouse effect probably began when Venus lost its water through atmospheric escape, eliminating the natural processes that normally regulate carbon dioxide concentrations. Earth's carbon cycle represents one of nature's most sophisticated regulatory systems. Plants absorb atmospheric CO2 during photosynthesis, converting it into organic matter. When organisms die, some carbon gets buried in sediments, effectively removing it from atmospheric circulation for millions of years. Volcanic activity and rock weathering release stored carbon back to the atmosphere, completing the cycle. Ocean absorption and release of CO2 provides additional buffering against rapid atmospheric changes. Water's unique properties extend far beyond its obvious importance for biological processes. Unlike most substances, water expands when it freezes, causing ice to float rather than sink. This seemingly simple characteristic prevents lakes and oceans from freezing solid from bottom to top, preserving aquatic life during cold periods and maintaining the global water cycle that distributes heat around the planet. The constant movement of water through evaporation, condensation, and precipitation drives weather patterns that make different regions habitable for different forms of life. Tropical rainforests exist because warm ocean temperatures create massive evaporation, which condenses into rainfall over land masses. Desert regions often form in rain shadows where mountains block moisture-laden air. Seasonal monsoons bring life-giving precipitation to billions of people across Asia and Africa. Yet water distribution remains precarious across much of our planet. While 71% of Earth's surface lies underwater, less than 3% of total water volume is fresh, and most of that remains locked in polar ice sheets and glaciers. Rivers, lakes, and groundwater that directly support human civilization represent less than 1% of Earth's total water supply. Human engineering has attempted to even out these natural inequalities through dams, reservoirs, irrigation systems, and water transport infrastructure. The Hoover Dam transformed the American Southwest by storing Colorado River water for millions of people. The California Aqueduct moves water hundreds of miles from northern mountains to southern cities and agricultural regions. Similar massive projects exist worldwide, from China's south to north water diversion to Australia's Snowy Mountains scheme. But these systems create new vulnerabilities alongside their benefits. Dam failures can catastrophically flood downstream areas. Prolonged droughts can empty reservoirs faster than they can refill. Changing precipitation patterns can reduce water availability in regions where millions of people have built their lives around engineered water security. Soil represents perhaps the most underappreciated component of Earth's life support systems. What appears to be simple dirt actually contains intricate communities of bacteria, fungi, insects, worms, and countless other organisms that break down organic matter, cycle nutrients, and create the chemical conditions necessary for plant growth. Healthy topsoil can take hundreds of years to develop naturally through the gradual breakdown of rock, accumulation of organic matter, and establishment of biological communities. Modern agriculture has dramatically accelerated soil degradation through intensive farming practices, chemical fertilizers, and monoculture cropping that reduces biological diversity. The Dust Bowl of the 1930s demonstrated how quickly productive agricultural land can become uninhabitable when soil systems collapse. Similar degradation continues today across many farming regions worldwide. Plate tectonics provides long-term climate regulation through the slow recycling of carbon between atmosphere, oceans, and rock formations. When oceanic plates sink beneath continental plates in subduction zones, they carry carbon-rich sediments deep into Earth's mantle. Volcanic eruptions release this stored carbon back to the atmosphere over geological timescales, helping maintain the delicate atmospheric composition that supports complex life. This geological carbon cycle operates over millions of years, much slower than biological and oceanic carbon cycling. But without it, Earth's climate would gradually drift toward extremes that would make surface conditions uninhabitable. Mars lacks active plate tectonics, which may explain why it lost most of its atmosphere and became the cold, dry planet we observe today. Every single breath you take connects you to an atmospheric story, spanning 4.5 billion years, and it's a story that's now reaching a critical turning point. Right now, as you read these words, your lungs are processing air that's chemically different from what any human breathed just 200 years ago. This isn't a gradual, natural shift occurring over millennia. We're witnessing the fastest atmospheric transformation in Earth's recorded history, and we're the primary cause. The thin layer of gases surrounding our planet extends roughly 10,000 kilometers above your head, but virtually everything that determines whether you can survive happens within the first 12 kilometers, a distance shorter than most people's daily commute. This narrow zone, called the troposphere, contains all weather, all breathable air, and all the atmospheric dynamics that regulate global temperature and climate patterns. Understanding what's happening to this atmospheric envelope requires recognizing that it functions as a living system, not just empty space filled with gases. Every molecule of oxygen you inhale was recently exhaled by a plant somewhere on Earth. Every carbon dioxide molecule you breathe out will likely be absorbed by vegetation within days or weeks. This constant exchange between biological organisms and atmospheric gases has maintained breathable air for millions of years through an intricate balance that's now being disrupted. The oxygen comprising 21% of our atmosphere represents one of the most remarkable success stories in planetary history. Before cyanobacteria began photosynthesis roughly 2.4 billion years ago, Earth's atmosphere contained virtually no free oxygen. These microscopic organisms gradually pumped oxygen into oceans and eventually into the atmosphere as a waste product of converting sunlight into chemical energy. This great oxidation event initially triggered a massive extinction, killing off most anaerobic organisms that found oxygen toxic. Yet this atmospheric catastrophe also enabled the evolution of complex life forms capable of using oxygen's high chemical energy for sophisticated biological processes. The same gas that eliminated primitive life became essential for everything from flying insects to thinking humans. Current oxygen concentrations represent another of Earth's precisely balanced systems. At 25% atmospheric oxygen, lightning strikes would ignite unstoppable global wildfires. As vegetation became explosively combustible, at 15% oxygen, large animals couldn't maintain brain function, and human consciousness would fade from oxygen deprivation. This narrow 21% concentration has remained stable for millions of years through the balanced exchange between photosynthetic oxygen production and biological oxygen consumption. But carbon dioxide, despite representing less than 0.05% of atmospheric volume, wields enormous influence over planetary habitability. This trace gas acts like a planetary thermostat, trapping just enough heat to keep Earth's average temperature above freezing while preventing runaway greenhouse effects that would make surface conditions uninhabitable. For the past 800,000 years, and a period spanning multiple ice ages and interglacial warm periods, atmospheric carbon dioxide concentrations fluctuated between roughly 180 and 300 parts per million. These natural variations corresponded to major climate shifts, but they occurred over thousands of years, allowing ecosystems time to adapt and migrate. Since 1950, atmospheric CO2 levels have skyrocketed past 420 parts per million and continue climbing at unprecedented rates. This increase directly correlates with human fossil fuel combustion, which releases carbon that was safely buried underground for millions of years. We're essentially conducting a massive uncontrolled experiment with Earth's atmospheric chemistry, with no clear understanding of all potential consequences. The warming effects of increased greenhouse gases trigger cascading changes throughout Earth's climate systems. Warmer air holds exponentially more moisture, intensifying storms and creating more extreme precipitation events. Changed temperature gradients disrupt jet stream patterns, causing weather systems to stall in place and creating prolonged heat waves, droughts, and flooding events. Arctic ice loss demonstrates how these feedback loops accelerate beyond human control. White ice surfaces reflect roughly 90% of incoming solar radiation back into space, helping maintain cooler global temperatures. As ice melts, darker ocean water absorbs 90% of solar energy, warming water temperatures and accelerating further ice loss. This feedback loop, once triggered, becomes increasingly difficult to reverse even if greenhouse gas emissions were immediately reduced. Permafrost thawing presents another accelerating feedback mechanism. Permanently frozen soils across Alaska, Canada, and Siberia contain roughly twice as much carbon as currently exists in the entire atmosphere. As temperatures rise, this frozen organic matter begins decomposing, releasing both carbon dioxide and methane greenhouse gas, more than 25 times more potent than CO2 over century-long timescales. Methane emissions highlight how multiple human activities compound atmospheric changes. Livestock agriculture produces methane through digestion. Rice cultivation generates methane in flooded fields. Landfills create methane as organic waste decomposes. Natural gas extraction and transport leak methane directly into the atmosphere. These sources combine to create methane concentrations that have more than doubled since pre-industrial times. Nitrous oxide represents another long-lived greenhouse gas primarily released through industrial fertilizer use and fossil fuel combustion. While less abundant than CO2 or methane, N2O persists in the atmosphere for over 100 years and contributes significantly to both greenhouse warming and stratospheric ozone depletion. Meanwhile, the natural systems that normally regulate atmospheric composition are being overwhelmed or destroyed. Forests act as massive carbon storage systems, absorbing CO2 during photosynthesis and storing carbon in wood roots and soil. Deforestation not only eliminates future carbon absorption capacity, but releases stored carbon when trees are burned or decay. Tropical rainforest destruction particularly concerns climate scientists because these ecosystems store enormous amounts of carbon while generating their own weather patterns. The Amazon rainforest produces approximately half of its own rainfall through transpiration. As deforestation reduces forest cover, this moisture recycling system weakens, potentially triggering irreversible transformation from rainforest to savanna across vast areas. Ocean carbon absorption demonstrates both nature's resilience and its limits. Seawater has absorbed roughly 30% of human carbon emissions, helping moderate atmospheric CO2 increases. But this service comes at tremendous cost to marine ecosystems. As oceans absorb CO2, chemical reactions make seawater more acidic, dissolving the shells and skeletons of countless marine organisms. Ocean acidification particularly threatens coral reefs, which support approximately 25% of marine species, despite occupying less than 1% of ocean area. Warmer, more acidic waters trigger coral bleaching events that can kill reef systems developed over thousands of years. Recent mass bleaching events have affected coral reefs worldwide, from Australia's Great Barrier Reef to Caribbean and Pacific island systems. Air quality degradation represents the most immediate human health consequence of atmospheric changes. Increased wildfire frequency fills air with particulate matter and toxic compounds. Rising temperatures worsen ground-level ozone formation, contributing to respiratory diseases. Changed precipitation patterns alter pollen production and extend allergy seasons. These atmospheric changes aren't gradual adjustments that human societies can easily adapt to over generations. They're rapid shifts that are already forcing immediate responses in agriculture, water management, coastal protection, and public health systems worldwide. For all the worry about greenhouse gases and melting ice, there's another truth worth pausing on: life itself functions as Earth's quiet regulator. It's easy to think of the biosphere as a set of forests, oceans, and animals existing atop the planet. In reality, it's inseparable from the planet's chemistry. Microbes in the soil, plankton drifting with the currents, fungi dissolving fallen leaves, trees rising toward the clouds, all of these are components of a vast interconnected system that actively modulates the atmosphere. Together, they recycle carbon, fix nitrogen, stabilize oxygen levels, and buffer climate shocks. This self-healing resilience has kept Earth habitable through events that appear almost unimaginable to us. Asteroid strikes, supervolcanoes, and periods when ice sheets reach the equator. Yet that resilience isn't infinite. It's bounded by thresholds. Scientists call these critical points, tipping points. Push a system far enough, and recovery is no longer possible. Instead of bouncing back, it snaps into another state entirely, often one far less compatible with human life. Consider the Amazon rainforest. Right now, it functions as one of the largest carbon sinks on the planet, sucking up billions of tons of CO2 and regulating rainfall across South America. But if it loses too much forest cover, it could tip into savanna, hotter, drier, and biologically poorer. Instead of pulling carbon from the atmosphere, it would start releasing massive amounts of it, accelerating warming globally. Or look at the Greenland ice sheet. Locked inside it is enough frozen water to raise global sea levels by more than 7 meters if it melted completely. Scientists warn that steady warming could push it past a point of no return, triggering irreversible melt. And if that happens, it won't simply flood coastlines. It could disrupt the Atlantic meridional overturning circulation, a major ocean current system that carries warmth from the tropics toward Europe. Shut that conveyor belt down, and weather patterns across entire continents would reorganize. Summers and winters in the northern hemisphere would look nothing like the seasons we know today. These are not isolated disasters. They're planetary scale shifts. The atmosphere doesn't recognize borders, neither do ocean currents or jet streams. What happens in the Arctic doesn't stay in the Arctic. A single tipping event can cascade into others, with one collapse feeding into the next. For decades, the phrase climate change has been described as a slow-moving crisis, something generations could prepare for. But in geological perspective, what's happening now is lightning fast. Atmospheric carbon hasn't spiked this quickly in millions of years. Species are disappearing at rates comparable to the asteroid strike that ended the age of dinosaurs. It's not that Earth can't adapt, it always has. It's that natural adaptation unfolds over thousands or millions of years. We're forcing changes in mere decades. When ecosystems can't keep pace, collapse follows. And yet, we aren't powerless in this story. Unlike any species that came before us, humans understand climate systems in extraordinary detail. We've mapped atmospheric layers, measured gases from both ancient ice cores and satellites orbiting overhead, and run sophisticated simulation models that forecast possible futures. With that knowledge, we've started to test solutions restoring forests that act as carbon sinks, deploying renewable energy to reduce emissions, and experimenting with technologies that pull carbon directly from the air. No single fix is enough, but together they form a toolkit for slowing and perhaps even reversing some damage. Still, science without action does little. The data are clear, atmospheric warming is underway, and human activity is the driver. What happens next rests less on knowledge than on collective decisions. But here's the paradox. While the science paints a sobering picture, the atmosphere itself remains astonishingly alive with movement and beauty. Walk outside, and it still greets you with the softness of a breeze, the rhythm of clouds, the chorus of birds echoing against it. This fragile system hasn't yet crossed the point of no return. Every breath you take is proof that the balance still holds minus for now. That air doesn't just hang above us like a passive blanket. It dances constantly. It sways trees, builds storms, and bends sound. It carries the smell of rain and the taste of salt from distant oceans. It's both invisible and deeply physical, brushing across your skin every time the wind shifts. And every inhale you take connects you to everything in it. Spores from fungi, microscopic bits of dust, traces of pollen, even molecules that once passed through the leaves of ancient forests. That's why changes in the atmosphere feel so personal. We know the sky not only by its light, but by its moods. A dense humidity before a summer storm, the sting of frost in the morning air, the clarity of a crisp autumn evening. Most of the time, weather is part of the background rhythm of life. We carry umbrellas or wear coats, maybe complain about the heat or cold, but there's usually a sense of predictability. What we expect is variation within limits. That sense of normality, however, is shifting, because weather is simply climate in motion. Sunlight unevenly strikes Earth, heating the equator more intensely than the poles. Warm air rises, cool air sinks, and those differences set the atmosphere in circulation. Winds stretch across continents, storms spin across oceans, currents swirl with planetary rotation, and local landscapes mold patterns further. Forests temper rainfall, deserts radiate heat, mountains divert passing winds. Out of all this variation, there's been a reliable order: monsoons in Asia, snow in the Rockies, droughts in the Sahel, but now that order is fraying. When scientists talk about climate change, they aren't describing the weather tomorrow or whether it rains next Tuesday. They're describing the long-term averages, the background rules shaping those daily conditions, and those averages are shifting in ways that redefine what we call normal. Winters arrive warmer, springs begin earlier, droughts stretch longer, heat waves last weeks instead of days. None of this lives in graphs alone. It manifests in daily life, in the way crops ripen, in the timing of floods, in the neighborhoods evacuated during fires. Heat is the clearest marker of change. The last decade has rewritten record books all over the world. Countries accustomed to mild climates find themselves battered with dangerous heat waves that linger far beyond what human health can handle. Cities across Europe, Asia, and North America now endure summers where temperatures soar above 40 degrees Celsius for days or weeks. In regions without reliable air conditioning or where power grids buckle under extreme demand, heat turns deadly, especially for the elderly, infants, outdoor workers, and people with health conditions. Extreme heat isn't just unpleasant, it's lethal. And heat's impacts ripple outward. Crops wilt in scorched fields, setting off food price spikes. Roads warp, runways soften, and railroads bend under thermal stress. Industrial processes slow or halt as cooling systems struggle. Wildfires feed off dried vegetation, now more abundant after long hot summers. Sparks from lightning or faulty power lines ignite infernos that generate their own weather systems. Firestorms can create columns of wind strong enough to mimic tornadoes, carrying embers for miles. At the other end of the spectrum, storms are growing more devastating. A warmer atmosphere holds more water vapor, which means when rain does come, it often comes in torrents. Tropical cyclones, hurricanes, and typhoons thrive on heat from ocean surfaces, and with oceans warming, storms now build faster, last longer, and unleash heavier rainfall. Surge waters push farther inland, while floodplains spill past boundaries established decades ago. Even where storm frequency hasn't risen, storm intensity clearly has. Flooding arises from multiple sources, powerful storms unloading more water than land can absorb, overwhelmed river systems, and earlier snowmelt caused by warmer winters. Each contributes to a landscape increasingly vulnerable to destructive inundations. This then is where Earth now stands. Life and atmosphere once worked together in a resilient, self-correcting system. But under mounting strain, those corrections falter, patterns bend, and new extremes begin to define the climate we live in. And still, in every breeze and every breath, lies a reminder that the balance meet as though fragile meet as ours, to protect or to lose. The signs are not subtle anymore. Streets that once only flooded during extraordinary storms now fill with water after routine rainfalls. Coastlines that for centuries felt secure now watch the sea creep inward, tide by tide. Rising sea levels don't just nibble away at beaches, they push salt water into drinking supplies, weaken foundations of buildings, and overwhelm the very systems designed to protect communities. Insurance companies recalibrate risk, premiums soar, and in some regions coverage disappears altogether, leaving families one storm away from financial ruin. Rebuilding grows harder every cycle, not because humans are less capable, but because the baseline conditions keep shifting beneath their feet. Elsewhere, the opposite story unfolds. Instead of too much water, there is not enough. Drought emerges either as a creeping shadow or a sudden sharp crisis. In some regions, it shifts rainfall away for years at a time until reservoirs fall to record lows and farmland cracks in the relentless sun. Farmers who once relied on centuries-old knowledge of planting seasons now struggle against patterns that no longer match memory or tradition. Crops curl and wither, harvests shrink, aquifers are drained faster than they recharge. In other places, drought slams down in just a few months, forcing governments to ration water, mandate restrictions, and make decisions about what survives the season: agriculture, industry, or cities. The silent danger of drought is how slowly it reveals itself. By the time it becomes undeniable, rivers are nearly dry, and ecosystems already on the edge stand collapsed. But instability is not limited to the extremes. The more subtle disruption arrives in the timing of transitions. Springs now awaken earlier. Snowpacks melt weeks ahead of schedule. Birds returning from migration find the insects they feed on have already peaked. Crops flower before pollinators arrive, leaving plants without partners for reproduction. What seem like minor misalignments accumulate into cascading consequences. Ecosystems that once thrived in synchrony begin to falter as once consistent signals no longer line up. High above, the atmosphere's own conveyor belts, the jet streams are changing shape. These narrow, high-altitude rivers of wind often dictate entire seasons of weather, Normally swift and relatively contained, they've begun to wobble more frequently. This wobbling means storms linger longer over some regions and scorching heat bakes others in place for weeks. A community that once expected a weekend storm now finds itself under a week-long siege of rain. A heat wave once measured in days now stretches deadly across half a month. The systems aren't necessarily occurring more often, but when they arrive, they refuse to leave, magnifying their destruction. What once counted as a rare catastrophe is happening with uncomfortable regularity. The thousand-year flood now strikes every couple of decades. Unprecedented has become a word repeated so often it edges on meaninglessness. Infrastructure designed for one version of climate is cracking under the load of another. Storm drains built for occasional surges overflow more commonly. Power grids not engineered for the heat of modern summers collapse under demand, leaving millions without the cooling that has become not just luxury but necessity. Asphalt buckles, rail lines warp. Even buildings groan under stress they were never meant to endure. For some regions, the changes creep in like background noise. Each summer just a little hotter, each winter a little shorter, each storm a little harsher. For others, the shifts arrive in devastating bursts, a single cyclone, a wildfire season that burns beyond memory, or sudden water scarcity that reshapes entire ways of life. Fragile nations built on narrow coastal strips or scattered islands confront the reality that their very geography is being erased. Larger coastal cities pour billions into seawalls, pumps and barriers, knowing these may buy time but not permanence. Farmers experiment with drought-resistant crops or abandon generations-old fields entirely. Communities relocate, often unwillingly, not just leaving soil behind but history, culture and identity as well. The physics that drive this crisis are well understood. Climate change doesn't invent storms out of nothing. It amplifies them. It doesn't conjure new droughts, but sharpens dry seasons into punishing scorchers. It doesn't create heat waves, but stretches them into killers. This is the amplification effect. Earth's old weather systems turned up louder, harsher, more destructive. 1 degree warmer makes storms hold more rain, makes summers grind longer, makes landscapes more combustible. The difference between survivable and catastrophic often hinges on margins measured in fractions. Yet not all responses are physical. There is a quieter damage as well, the mental and emotional cost of living in a world where safety feels more provisional. When homes burn in wildfires, survivors don't just lose possessions, they lose the sense that the land itself will welcome them tomorrow. When rivers overflow or storms surge through neighborhoods, rebuilding means confronting grief, anxiety, and the haunting knowledge that it might happen again, sooner than expected. Communities carry these invisible scars as surely as they carry financial losses. Psychologists now recognize climate anxiety, not just in children fearing the future, but in adults who have lived through disaster after disaster. Restoration requires not just bricks and roads, but trust, security, and memory of stability. Then comes the sobering question: how hot is too hot for human life? The answer arrives in something called wet bulb temperature. Unlike simple thermonodes, this measure combines air heat with humidity. At about 35 degrees Celsius wet bulb, even the healthiest human working in the shade with water for hydration cannot cool their body through sweat. Organs overheat, strain and fail. Death becomes a matter of hours. And terrifyingly, some regions are flirting with this boundary already. Heat waves in South Asia and the Middle East have already approached wet bulb conditions for brief periods. Entire populations risk days each year, when human survival outdoors is virtually impossible. These figures are not hypotheticals. They're recorded, which makes the question not theoretical. What happens as these days go from occasional to frequent? Even as the world works on mitigation, renewable energy emissions targets, reforestation projects, improved climate modeling, the weather itself refuses to pause. The atmosphere doesn't wait for policy. Temperature records don't hold for negotiation. The storms come on their own schedule, yet knowledge still makes a difference. Better forecasting saves lives. Revised building codes reduce destruction. Communities restoring wetlands provide buffers against floods. Cities redesigning streets to channel wind or investing in reflective roofs reduce heat stress. Managed forests reduce wildfire intensity. These adaptations don't halt the warming, but they grant precious time, time in which bigger systemic changes might take hold. Weather has always shaped human history. It determined where riverside civilizations could thrive, how crops spread between continents, how armies marched or failed during campaigns. Today it plays an even larger role, because the weather itself is shifting at scales and speeds unseen before. To endure now demands more than umbrellas or storm drains. It demands understanding the feedback loop we're tangled in. Our emissions alter the altered air reshapes weather reshapes our societies, and those societies either strengthen their response or further the imbalance. So the question changes subtly but significantly. It's no longer only whether Earth will stay habitable, it's which regions will remain livable, for how long, and what those changes will demand of the billions alive. Who chooses where to build, where to retreat, or which communities endure hardship first? These aren't just scientific questions, they're societal ones, political ones, even moral ones. And looming over all of it is the carbon clock, ticking constantly in the background. Carbon dioxide might feel intangible, invisible, almost trivial when thought of as mere parts per million, but its consequences are lasting. It's the most abundant greenhouse gas humans release. It lingers longest in the atmosphere, a single emission today remaining for centuries, warming future generations not yet born. Methane and other gases burn shorter, quicker scars. Carbon dioxide endures. Each ton emitted now becomes part of tomorrow's climate, baked into the baseline from which humanity must work. Like a kettle approaching its boil, pressure builds quietly, often underestimated until the moment of threshold. Climate is no different. It accumulates lethally slow until one day the signal isn't numbers in a report, but streets underwater, crops withering, or air too hot to inhale. By then, the clock's ticking is no longer background, but alarm. When we burn coal, oil, and natural gas, we're not just producing energy, we're reintroducing carbon from an ancient vault that was sealed off millions of years ago. Think of it as breaking open a bank account that nature never meant for us to touch. For over a century now, humanity has been spending down that account like there's no tomorrow, pouring fossil carbon into the sky where it doesn't belong. And the result has been unmistakable: the sharpest spike in atmospheric carbon dioxide in geological history. The moment industrial smokestacks began billowing in the 18th and 19th centuries, the chemistry of the atmosphere started to shift. But it wasn't until 1958, when Charles David Keeling set up his monitoring station high above the Pacific on Mauna Loa, that the evidence became undeniable. His measurements produced what's now called the Keeling curve, a line climbing year after year, with a jagged sawtooth shape reflecting the seasons as forests breathed in spring and exhaled in autumn. That curve has never flattened. It has only risen decade after decade, turning into one of the most iconic graphs in science and one of the direst warnings we've ever received. For most of human existence, atmospheric carbon dioxide hovered around 280 parts per million. Civilizations flourished under that steady backdrop, but within just a few decades, it surged. By the year 2000, the concentration passed 370 ppm. Today it has exceeded 420 ppm, and still it ascends. The difference may sound small when reduced to numbers, but climate is not a system that tolerates even small shifts without response. The last time the planet experienced this level of carbon, seas were meters higher and global temperatures were several degrees hotter. Humans didn't yet exist in that world. And Celery 2 is just the beginning. Methane adds another layer of urgency. Molecule for molecule, it traps heat over 80 times more effectively than carbon dioxide across a 20-year timescale. Its concentrations have more than doubled since the dawn of the Industrial Age, fueled by livestock emissions, thawing permafrost, rice paddies, leaky pipelines, and landfills. Then there's nitrous oxide released from nitrogen fertilizers, industrial processes, and combustion. Though less frequently discussed, its warming potential is nearly 300 times that of carbon dioxide when considered over a century. Together, these gases create a thermal imbalance. More energy enters Earth from the sun than escapes back into space. This difference, what scientists call radiative forcing, is measurable, observed from satellites, ground stations, and climate models that consistently reveal the same truth. Earth is trapping more heat than it releases. To keep that imbalance within safe limits, scientists use a concept called the carbon budget. It's not abstract. It's a calculation of how much more carbon dioxide humanity can still emit before crossing dangerous thresholds of global warming. Thresholds like 1.5 degrees Celsius and 2 degrees Celsius above pre-industrial temperatures. These aren't arbitrary markers. They're based on risk. At 1.5 degrees Celsius, we lose most coral reefs, heat waves become routinely deadly, Arctic ice shrinks dramatically, and many low-lying coastal regions face creeping inundation. At 2 degrees Celsius, those risks intensify sharply, sea levels rise faster, extreme weather grows deadlier, and ecosystems tip closer toward collapse. The sobering reality: we've already consumed most of the budget for staying below 1.5 degrees Celsius. What's left is vanishing quickly. Each year of high emissions eats away at the margin, making the task harder. And here's the cruel twist. The difference between 1.5 degrees Celsius and 2 degrees Celsius may sound like half a degree, but in practice it's the difference between vulnerable regions struggling and outright failing. It's the difference between millions displaced and tens of millions displaced, between unbearable days and unlivable summers. Climate impacts don't increase gradually with warming, they surge. Not every source of emissions contributes equally. Energy production, especially burning fossil fuels for electricity and heating, is the single largest culprit. Transportation adds another massive slice. Cars, trucks, ships, airplanes, all still heavily dependent on oil. Industry contributes too, with steel and cement in particular producing unavoidable CO2 as part of their chemical processes. Agriculture is another powerhouse of emissions, especially through methane from livestock and nitrous oxide from fertilizers. Even buildings play a part in how we heat, cool, and light them, often inefficiently. Yet every one of these sectors holds solutions: cleaner fuels, smarter efficiency, electrification where possible, smarter design that requires fewer resources. In transportation, electric vehicles and greener fuels are expanding. In industry, scientists are experimenting with alternative steelmaking that avoids coal and lower carbon cement formulas. In agriculture, shifts toward regenerative farming seek to restore soil carbon. Even meat substitutes and lab-grown protein enter the discussion as part of reducing methane-heavy livestock herds. But solutions take time, scale, and willpower. And time is the one thing carbon makes scarce. The carbon dioxide emitted today will be warming the atmosphere a century from now. Reducing emissions is critical, but so is considering ways of pulling carbon out of the atmosphere. Reforestation remains the most natural solution, one humanity has understood for centuries. Trees drawing in carbon as they grow, storing it in roots, trunks, and soil. Wetlands and peatlands also act as vast, quiet carbon banks. Beyond nature, new technologies are emerging. Direct air capture machines that vacuum carbon directly from the sky. Bioenergy systems that burn plant matter for energy, but capture emissions before they escape. Farming methods that increase soil's ability to lock away carbon. These methods are promising, but none are silver bullets. Direct air capture operates in pilot plants but remains enormously costly. Forests take decades to mature, and in a hotter world they're increasingly vulnerable to fire and drought. Bioenergy risks competing with food production. Scientists agree carbon removal is necessary, but it cannot substitute for reduction. Trying to mop the floor while the tap is still gushing only makes sense if the leak is already sealed. And then there's the challenge of fairness. One of the most glaring realities of climate change is that the regions most devastated are rarely those most responsible. Wealthy nations, having burned the majority of fossil fuels during their industrial rise, have emitted lion's shares of historical carbon. Yet it is low-income nations in fragile geographies, small islands, arid regions, dry tropics, that face the sharpest consequences. These nations often lack infrastructure, medical systems, and financial resources to cope with intensifying disasters. Meanwhile, wealthy countries can buffer themselves with stronger buildings, advanced forecasting, and emergency response capabilities. The result is a dangerous imbalance. Those least responsible suffer the most. International negotiations like those hosted under the UN Framework Convention on Climate Change attempt to address this injustice. Agreements often call on developed nations to finance adaptation and mitigation in developing ones. Promises flow from podiums, billions pledged, some delivered, some delayed. Meanwhile, seas continue to rise, heat stress continues to grow, and time continues to shrink. Global diplomacy moves slow, while the atmosphere responds fast. Yet signs of progress exist. Nations are pouring record investments into renewable energy, solar, wind, hydro, and increasingly storage technologies. Electric vehicle adoption accelerates. Companies experiment with carbon-neutral targets. Whole economies are beginning to bend around the idea that survival depends on transformation. But scale remains everything, and every year of delay narrows the path forward. Because here's what sets climate change apart from so many crises: it doesn't stop the moment we stop feeding it. Every ton of carbon emitted remains active in the system for centuries. Stabilizing the climate requires halting the growth of emissions, while simultaneously removing what's already accumulated. That lag effect, that delay between cause and consequence, is why timing is everything. So the question circles back not just to science or technology, but to choices. How much carbon will we still release before the budget runs dry? How fast will we commit to alternatives before thresholds tip? For every year of hesitation, for every delay in ambition, the carbon vault that humanity keeps unlocking adds another entry to the atmosphere's permanent ledger. And while atmospheres don't negotiate, humans can. The challenge is whether we'll do it in time. Would you like me to continue into Section 8, where we take this further from emissions and energy systems specifically into oceans, rising, acidifying, and warming as Earth's largest heat and carbon sink? That keeps the narrative progressing naturally. What if everything you thought you knew about climate change was only half the story? While everyone focuses on melting glaciers and rising temperatures, there's a massive system covering 3/4 of our planet that's been quietly absorbing the real damage. This invisible force has been protecting us from catastrophe, but it's reaching its breaking point, and when it fails, the consequences will reshape civilization as we know it. Renewable energy costs have plummeted below traditional fuel prices across numerous global regions. Electric transportation gains momentum daily. Metropolitan areas revamp construction standards to slash carbon output. Corporations establish environmental goals. People minimize consumption, preserve resources, and embrace eco-friendly alternatives. Every action contributes, yet these efforts must accelerate dramatically to alter our trajectory. Maintaining optimism becomes challenging when statistics continue climbing. However, the carbon timekeeper isn't a doomsday countdown. It serves as an instrument showing remaining opportunities to redirect our path. This applies beyond policymakers to every individual. Decisions made during upcoming years will determine the world future generations will inherit. While this responsibility feels overwhelming, such weight shouldn't breed hopelessness. Instead, it can provide focus, creating collective awareness of priorities and possibilities. Our atmosphere remains salvageable rather than lost. It functions as a responsive mechanism reacting to human intervention. The same acceleration patterns driving environmental destruction can equally amplify restoration efforts. When emissions decline, vegetation expands and systems transform. Time continues moving, yet hasn't expired. Standing on coastal shores gazing across waters, the ocean appears motionless. Waves approach and retreat, while tides follow predictable cycles. Beyond visible horizons, vast waters maintain perpetual movement. These deep, expansive forces silently influence planetary climate patterns. Encompassing over 70% of Earth's surface, oceans represent crucial systems regulating temperatures, storing thermal energy, and distributing heat globally. They capture approximately 90% of excess warmth trapped by greenhouse emissions, serving as buffers preventing rapid atmospheric heating. Without this protection, air temperatures would skyrocket while climate patterns became extremely unstable. This essential service demands significant sacrifice. Heated water expands, causing ocean levels to climb as temperatures increase. Dissolving ice contributes additional volume. Combined effects push shorelines progressively inland. This elevation isn't consistent everywhere. Regional factors, underwater flows, and gravitational forces create varying impacts across different locations. Nevertheless, the overarching pattern remains unmistakable. Waters ascend gradually yet persistently. Sometimes coastal ground simultaneously subsides, magnifying these consequences. Waterfront populations already witness these transformations. Elevated tides penetrate deeper territories. Flooding previously occurring once per decade now strikes annually or biennially. Saltwater infiltrates freshwater sources and farming regions. Some areas measure changes in centimeters. Others calculate impact through reconstruction frequency. Consider the underwater highways, enormous aquatic rivers transporting warm and cool waters between continents. These flows critically regulate worldwide climate stability. The Gulf Stream exemplifies this phenomenon, carrying tropical warmth toward the North Atlantic, maintaining European temperatures far milder than latitude alone would permit. Southern Hemisphere features the Antarctic circumpolar current, continuously circling the globe unobstructed, linking oceans while regulating thermal and carbon distribution. These currents operate through wind power, planetary rotation, plus temperature and salt concentration differences, a mechanism called thermohaline circulation. Dense, salty, cold water descends, drawing warmer surface water poleward as replacement. This conveyor belt arrangement stabilizes climate through planetary energy distribution. Unfortunately, this system weakens progressively. Scientific research reveals portions of this global oceanic conveyor are deteriorating, particularly within North Atlantic regions. Freshwater from dissolving Greenland ice reduces salt levels, disrupting the sinking process, powering these currents. Continued degradation could trigger extensive ramifications, modifying weather systems, transforming precipitation patterns, and elevating water levels along American East Coast and Western European territories. Previous significant weakening occurred during the last glacial period's conclusion, causing sudden climate disruptions. Beyond heat transportation, oceans store substantial portions of atmospheric carbon dioxide. Phytoplankton, microscopic plant-like organisms dwelling near surfaces, absorb CO2 through photosynthesis. Upon death, some carbon descends into deep waters, effectively sequestering it for centuries. Rising temperatures and increasing acidity reduce this process's effectiveness. Ocean acidification presents another widespread challenge. Dissolved CO2 creates carbonic acid, reducing water pH levels. This transformation affects creatures constructing shells and skeletal structures from calcium carbonate, including corals, oysters, clams, and numerous plankton varieties. Increasing acidity makes growth and survival increasingly difficult for these organisms. Since they often anchor food webs, their population decline creates ripple effects impacting fish, seabirds, and humans dependent on marine protein sources. Warming and acidification effects appear most dramatically in coral reef ecosystems. These underwater communities, frequently termed oceanic rainforests, sustain remarkable biodiversity. They supply nourishment, protection, and reproductive habitats for innumerable marine species, while shielding coastlines from storm surges and erosion. Corals demonstrate extreme sensitivity to environmental changes. Excessive temperatures force them to expel symbiotic algae providing energy and coloration. This phenomenon creates coral bleaching. Persistent heat exposure results in death. Recent decades witnessed increasing mass bleaching episodes affecting extensive reef areas worldwide, including Australia's Great Barrier Reef. Recovery remains achievable when conditions improve, but repeated or extended stress pushes reefs beyond survival thresholds. Some already transition into alternative ecosystems, less diverse, less colorful, less capable of supporting previously dependent species. In deeper waters, far from sunlight penetration, additional transformations unfold. Surface warming creates stronger barriers between water layers, preventing oxygen mixing from surface to depth. Oxygen concentrations drop across many oceanic regions, generating zones where few organisms survive. These low oxygen areas, occasionally termed dead zones, also receive fuel from agricultural nutrient runoff. The convergence of temperature increases, chemical changes, and human pollution creates cascading effects throughout marine ecosystems, ultimately impacting every aspect of ocean health and functionality. This intricate system that has protected our planet for millennia now faces unprecedented pressure, and understanding its vulnerabilities becomes essential for comprehending our climate future. Agricultural chemicals flow downstream into waterways. Waterways transport nutrients toward marine environments where explosive algae growth occurs. Decomposing algae consume available oxygen, creating lifeless aquatic zones. These mechanisms interweave complexly. Temperature increases, chemical alterations, oxygen depletion, and contamination combine unpredictably, yet the trajectory remains evident. Aquatic environments face mounting pressure, and struggling ecosystems impact dependent human populations. Over 3 billion individuals depend on seafood as primary protein sources. Numerous coastal economies rely on recreation, fishing industries, and maritime commerce. Oceanic transformations directly affect these livelihoods. Fish populations migrate toward cooler territories. Harvest quantities diminish. Coral destruction reduces visitor attractions. Harbor facilities require redesign accommodating elevated water levels and intensified storm impacts. Adaptation initiatives are emerging. Marine conservation zones expand, providing ecosystem recovery opportunities. Sustainable fishing methods gain adoption across certain areas. Coastal municipalities construct protective barriers, rehabilitate wetlands, and establish buffer territories. However, like most climate adjustments, these endeavors must accelerate matching transformation rates. Growing attention focuses on rehabilitating natural climate solution ecosystems. Mangroves, salt marshes, and seagrass meadows capture and sequester substantial carbon quantities while protecting shorelines from erosion and storm destruction. Reconstructing these environments serves dual purposes as climate strategy and biodiversity conservation. Restoration requires significant timeframes, and irreversible damage exists. Current changes may persist for centuries. Water level elevation proves particularly challenging to reverse. Even immediate emission cessation wouldn't prevent continued thermal expansion and ice dissolution, adding volume for extended periods. This reality shouldn't inspire despair but emphasize present moment importance. Every temperature fraction matters. Each delayed year compounds future difficulties. Oceans seem separate, vast, profound, remote. Yet they influence everything: weather formation, temperature regulation, food provision, carbon absorption, and life sustenance. Constant movement occurs beyond observation. Accelerated changes demand greater human response. Rising waters haven't peaked. Future developments depend on our reactions, not merely to flooding but to constructed systems beside them. Metropolitan areas, harbors, economies, communities, all connected to warmer, fuller, more turbulent seas than existed previously. We now examine inland transformations, rainfall shaping forests, soil feeding billions, ecosystems maintaining equilibrium fragments. Our journey continues terrestrially, where vegetation, agriculture, and underground foundations reveal their climate narrative portions. Climate accounts don't always start with meteorological data or emission graphs. Some originate underground, handling dark, fertile earth, traversing forests after precipitation, or standing beside harvest-ready farmland reveals planetary components holding more than existence. They maintain equilibrium. Despite emissions and energy focus, ground conditions matter significantly beyond general recognition. Soil transcends simple dirt. It lives as complex structured habitat comprising minerals, decomposed matter, atmosphere, moisture, fungi, bacteria, and innumerable microscopic life forms. Single handfuls contain more microorganisms than Earth's human population. This concealed subterranean realm centrally influences food cultivation, water retention, carbon sequestration, and environmental stability. Healthy soil anchors vegetation, filters moisture, recycles nutrients, and feeds terrestrial food web foundations. When functioning properly, it operates silently and dependably. Deterioration creates expanding consequences. Farming depends on ground capable of moisture retention, proper drainage, erosion resistance, and plant growth support. Agricultural practices simultaneously apply pressure through intensive cultivation, single crop planting, artificial fertilizers, and excessive pesticide application, degrading structural integrity and microbial communities. Progressive deterioration causes compaction, nutrient depletion, and increased drought and flood susceptibility. Certain regions witnessed fertile territory becoming barren, making cultivation increasingly difficult each growing season. This degradation includes climate implications, soil losing decomposed plant and animal matter, carbon-rich organic material simultaneously loses carbon storage capacity. Disturbed Earth releases atmospheric carbon dioxide, accelerating warming trends. Elevated temperatures trigger more frequent droughts and severe weather, further degrading soil quality. This cycle develops gradually, yet carries substantial consequences. Trend reversal methods exist. Techniques including no-tillage farming, cover cropping, composting, and crop rotation rebuild organic content while restoring microbial diversity. These methodologies comprise regenerative agriculture, systems designed beyond harm minimization toward active land improvement. Some farmers already experience advantages: enhanced productivity, improved drought resistance, reduced input expenses. Adoption varies, while scaling requires time, support, and policy modifications. Forests critically maintain planetary equilibrium, covering approximately 30% of terrestrial surface. They function as carbon reservoirs, water regulators, climate stabilizers, and biodiversity sanctuaries. Trees capture atmospheric carbon dioxide through photosynthesis, storing it within wood and soil while releasing oxygen. Mature forests exceed simple tree collections. They represent interconnected root, fungi, animal, and microbe systems collaborating in gradual biological coordination. Tropical rainforests, including Amazon, Congo Basin, and Southeast Asian jungles, prove especially significant. They contain enormous carbon and moisture quantities, influence worldwide precipitation patterns, and support substantial planetary biodiversity portions. However, they face mounting pressure. Deforestation driven by timber harvesting, agriculture expansion, mining operations, and infrastructure development continues at scales difficult to monitor in real time. Cleared or burned forests release stored biomass carbon, transforming carbon absorbers into carbon emitters. Amazon research reveals forest sections potentially approaching critical thresholds. Beyond these points, ecosystems may transition irreversibly from moisture-generating rainforests to drier savannas. Such transformation would release massive stored carbon while eliminating crucial rainfall regulation affecting regional and global weather patterns. Temperature increases, precipitation changes, and extreme weather intensify forest stress. Droughts weaken trees, making them vulnerable to disease, insect infestations, and wildfire. Shifting climate zones force species migration or extinction when adaptation proves impossible. Indigenous communities stewarding these territories for generations possess valuable forest management knowledge. Their traditional practices often maintain ecosystem health while providing sustainable livelihoods. Supporting indigenous land rights and management systems represents both conservation strategy and social justice priority. Reforestation and afforestation efforts expand globally, yet restoration complexity exceeds simple tree planting. Successful forest rehabilitation requires appropriate species selection, consideration of local conditions, long-term maintenance, and community involvement. Young forests require decades reaching maturity and full carbon storage potential. Urban forestry gains recognition for climate benefits. City trees reduce temperatures through shade and evaporation, improve air quality, manage stormwater, and enhance mental health. Green infrastructure becomes an essential adaptation strategy for metropolitan areas facing increasing heat and precipitation extremes. Agricultural systems worldwide face mounting challenges, requiring fundamental transformations to maintain productivity while reducing environmental impact. Precipitation patterns transform while temperatures escalate, causing certain territories to become increasingly arid, experiencing more frequent combustion and losing regenerative capabilities. Continued deterioration could trigger forest transitions towards savanna-like conditions featuring diminished carbon sequestration and reduced species diversity. Such alterations would generate worldwide ramifications extending beyond local impacts. Beyond tropical zones, boreal woodlands spanning Canada, Scandinavia, and Russia contain enormous carbon reserves, particularly within their soil layers. These environments face escalating vulnerability to wildfires, insect invasions, and climbing temperatures. Northern region blazes release tree carbon plus deep soil carbon, especially peat that burns gradually and resists extinguishing efforts. Planetary warming increases fire frequency and control difficulty. Tree cultivation receives frequent promotion as remedy, proving helpful in specific situations. However, not every planting initiative achieves equal effectiveness. Installing non-indigenous species, single variety plantations, or vegetation in originally non-forested ecosystems can damage biodiversity, modify water cycles, and displace local populations. Forest restoration and establishment succeed optimally when rehabilitating native varieties, supporting regional ecosystems, and integrating with additional land utilization priorities. Meanwhile, agriculture and woodland balance grows increasingly strained. Expanding global population and dietary changes drive increased territory clearance for cultivation and livestock. Approximately 80% of worldwide agricultural territory produces meat and dairy products, despite representing under 20% of global caloric intake. Minimizing food waste, enhancing existing farmland productivity, and moderately adjusting consumption patterns can reduce woodland pressure while liberating territory for restoration or conservation. Land ownership questions arise. Who possesses territory? Who controls decisions? Whose interests receive priority? Indigenous communities manage or safeguard substantial portions of remaining global forests and biodiversity concentration areas. Research demonstrates that recognizing indigenous territorial rights typically correlates with reduced deforestation rates and superior ecosystem maintenance. Nevertheless, these populations frequently encounter legal, political, and economic pressures undermining their stewardship capabilities. Even modest ecosystems wield disproportionate influence. Grasslands, wetlands, savannas each contribute to carbon storage, water cycling, and life support. Wetlands particularly excel as carbon storage powerhouses, water filtration systems, and coastal buffers. Similar to forests, they've experienced drainage, filling, or degradation across numerous regions, especially for development and farming purposes. Underground territories possess quiet leverage. Soil, woodlands, and agricultural areas transcend passive climate story backgrounds. They actively participate. They absorb, release, adapt, and transform. Operating on human scales, meters rather than atmospheres, seasons instead of centuries, provides genuine influence opportunities. Technology offers assistance through satellite deforestation monitoring, to precision agriculture reducing fertilizer consumption. Policy contributes via subsidies supporting sustainable practices, conservation incentives, and trade regulations discouraging environmental damage. Much work remains practical and grounded, occurring on farms within forests through people planting, tending, harvesting, and protecting. Climate transformation will render some territories less productive. Droughts, heat waves, flooding, and shifting pest populations will challenge traditional farming methods. However, land can contribute solutions through increased carbon storage, efficient food production, and damaged ecosystem restoration. No singular solution exists, yet momentum builds, regenerative agriculture expands, forest protection increases, wetland restoration progresses. Required knowledge isn't novel, often recovering traditional farming techniques, local observations, and long-practiced stewardship methods. Forward paths won't prove simple but remain visible through existing change seeds. Food cultivation approaches, soil care methods, standing forests, and potential forest returns. They exist within current decisions made quietly across fields, hills, and woodland edges. Decisions shaping not only territory but surrounding air, water, and climate. Discussing extinction often evokes dinosaur imagery, creatures temporally distant, nearly mythical. Their sudden vanishing linked to asteroid impacts and cascading planetary disruptions represents history's most famous extinction event. Yet it wasn't initial or most severe. During the past 500 million years, Earth experienced 5 major mass extinctions, moments when species loss rates dramatically exceeded normal background levels, repeatedly reshaping life's evolutionary tree. Growing evidence suggests we're entering the 6th extinction phase. Extinction naturally occurs within life processes. Species emerge, adapt, evolve, and eventually vanish. Under typical circumstances, this proceeds gradually, few species lost across centuries or millennia. Mass extinction definition encompasses not merely lost species quantities, but elimination speed and ecosystem breadth. It compresses time, creating sharp biodiversity drops, leaving worlds noticeably emptier. Currently, species vanish at rates estimated between 100 and 1,000 times above normal levels. This doesn't indicate daily mass die-offs, but means extinction's background frequency has intensified, becoming more constant and harder to dismiss. Many scientists believe we're experiencing sixth mass extinction early stages, driven not by volcanic eruptions or asteroid strikes, but human activities. Causative factors are well documented. Habitat destruction leads as primary driver. Cleared forests, drained wetlands, and plowed grasslands eliminate or fragment wildlife spaces. Even remaining territories may become isolated by transportation routes, surrounded by agricultural development, or too degraded supporting original inhabitants. Contamination contributes significantly. Pesticides, heavy metals, plastics, and agricultural runoff enter ecosystems, altering life's delicate chemical balance. Marine environments absorb excess atmospheric carbon, increasing acidity levels. Waterways collect nutrients, fueling dangerous algal proliferation. Atmospheric particulates modify everything from insect behaviors to mammalian respiratory function. Overexploitation presents another threat. Hunting, fishing, and harvesting species faster than reproductive replacement. Some practices operate industrially while others remain locally subsistence-based. Both approaches can devastate populations when sustainable limits are exceeded. Climate transformation adds additional pressure. Temperature shifts, precipitation pattern changes, and extreme weather events force species beyond adaptation capabilities. Arctic ice melting eliminates polar bear hunting grounds. Coral bleaching destroys reef ecosystem foundations. Shifting agricultural zones push both human communities and wildlife into unfamiliar territories. Invasive species introduction creates ecological disruption. Human transportation accidentally or intentionally moves organisms between regions where they lack natural predators or competitors. These introduced species can overwhelm native populations through direct competition, predation, or ecosystem modification. Disease transmission accelerates through habitat fragmentation and increased human-wildlife contact. Stressed animal populations show greater vulnerability to pathogens, while reduced genetic diversity limits immune system effectiveness. Urban expansion fragments natural habitats into isolated patches, insufficient for maintaining viable populations. Many species require large territories for breeding, feeding, or seasonal migration. Habitat corridors connecting protected areas become essential for wildlife movement and genetic exchange. Conservation efforts face mounting challenges requiring innovative approaches, international cooperation, and substantial resource commitment to prevent further biodiversity collapse. International markets drive some exploitation while local needs fuel others. Outcomes remain identical. Population numbers decrease, breeding cycles fragment, and previously abundant animals start disappearing. Introduced species create additional complications. Global human movement carries organisms along, deliberately or accidentally. Rodents travel aboard vessels. Insects hitchhike within shipments. Decorative plants establish dominance after introduction. Most transplanted organisms struggle to survive, yet some thrive and outcompete indigenous varieties, disrupting ecosystem equilibrium. Damage doesn't always appear dramatically, sometimes subtly, gradually reshuffling territorial inhabitants until critical elements vanish permanently. Climate transformation presents the final pressure. Escalating temperatures, seasonal shifts, and modified weather force species to relocate, evolve, or perish. Some can adjust territorial ranges while others cannot. Certain species evolve rapidly. Others prove too specialized, sluggish, or already compromised by existing threats. Environmental changes alter food availability, migration pathways, and breeding seasons, creating widening gaps between species requirements and environmental provisions. Particular groups demonstrate heightened vulnerability. Amphibians, frogs, toads, salamanders show exceptional sensitivity to environmental modifications. Many already face endangerment. Insects, frequently overlooked, experience widespread population and diversity declines. Birds, depending on specific migration corridors or environments, struggle adapting to transforming conditions. Coral ecosystems, previously discussed, suffer bleaching and mortality. Larger creatures from elephants to whales confront poaching, territory loss, and reproductive slowness combinations, placing them at risk. Extinction transcends individual species loss. It dismantles interconnected networks. Every organism functions within broader systems. Vegetation feeds insects. Insects pollinate agriculture. Birds manage pest populations. Predators maintain prey balance. Single component disappearance triggers others to compensate, yet limits exist. Excessive species loss causes web deterioration. Biodiversity supplies resilience. Multi-species ecosystems better absorb disturbances, adapt to modifications, and recover from disruptions. They maintain clean water, productive soil, pollination services, and disease management. Diversity erosion makes ecosystems fragile and collapse-prone under pressure. Sixth, mass extinction concepts carry practical implications beyond academic interest. Food systems depend on pollinators. Medications derive from natural compounds. Economies require stable ecosystems. Beyond utilitarian needs exists shared heritage recognition, understanding our participation in something vastly more complex and magnificent than ourselves. Species loss diminishes both natural environments and our comprehension of them. Nevertheless, cautious language remains warranted. Scientific consensus on timeline and severity varies. Some argue threshold crossing hasn't occurred. Current rates, while concerning, remain below historical mass extinction levels. Others contend we're experiencing early phases with worse consequences approaching. Regardless, transformation direction appears clear. Species declining, habitats contracting, pressures intensifying. Hope persists through proven conservation effectiveness. Protected territories stabilize populations. Habitat corridors facilitate species movement. Captive breeding programs rescue animals from extinction brinks. International agreements like CITES regulate endangered species commerce. Local communities, indigenous populations, and citizen scientists contribute through often underreported methods. Global life cataloging efforts expand using new technologies enabling faster species discovery than previously possible. Some discoveries involve microscopic organisms, microbes, fungi, insects. Others include larger specimens, birds, mammals, deep-sea creatures. Many remain unnamed. Understanding existing biodiversity improves protection possibilities. Conservation approaches shift from single-species focus toward entire ecosystem preservation, recognizing no creature exists independently. Forests, reefs, wetlands represent true conservation units supporting wildlife and dependent human communities. Recent terminology includes rewilding and restoration, efforts transcending preservation to recovery, what was lost through species reintroduction, ecosystem rebuilding, and providing nature-healing space. These complex, sometimes controversial projects offer alternative frameworks, rebuilding abundance rather than merely fighting loss. Sixth, mass extinction continuation won't occur instantaneously, but unfold across years and generations through gradual erosion becoming increasingly visible over time. This timeline provides opportunity, not unlimited or wasteful time, but sufficient for course correction. Recognition begins with biodiversity value acknowledgement. Not merely catalogue entries, but living foundations sustaining our systems. This requires attention, coordination, and humility, while questioning whether worlds quieter in birdsong, emptier of woodlands, and lonelier in wilderness can truly remain habitable. Discussion now turns towards constructed elements, relied upon machinery, and systems maintaining our functioning world. Technology currently shapes planetary conditions as extensively as nature once did, with shadows and promises reaching every climate story corner. Throughout most human history, survival meant adapting to natural elements, weather, seasons, predators, soil conditions. We developed observation, prediction, and environmental collaboration skills. Time brought tools, tools enabled machinery, and eventually we began shaping surroundings more than they shaped us. Modern existence, electricity, transportation, communication, food networks, clean water, depends on technology operating quietly until malfunctions occur. These innovations accomplished extraordinary achievements, extending lifespans, reducing distances, connecting billions and making daily survival predictable. We've captured energy from coal, petroleum, gas, atoms, wind, solar and water sources, while constructing roads, satellites, networks, and urban centers. Each progressive step carried environmental costs through emissions, extraction, waste, and ecological disruption. Energy consumption initiated these impacts. Industrial revolution relied primarily on coal, later incorporating oil and natural gas. Fossil fuels provide concentrated, portable, dependable energy, essentially preserved sunlight from ancient organisms compressed over millennia. Combusting these resources enabled large-scale manufacturing, transportation, and electrical generation, while beginning massive atmospheric carbon dioxide releases. Contemporary machinery, automobiles, aircraft, factories, power facilities, operates on this energy. Globally, approximately 80% of world energy still originates from fossil sources. Every energy utilization stage, extraction, refinement, transport, combustion, contributes greenhouse gas emissions. Beyond direct burning, fossil fuel infrastructure requires extensive development, drilling platforms, pipelines, refineries, distribution networks. Each component demands materials, construction, maintenance, and eventual replacement, multiplying environmental impacts. Manufacturing processes consume enormous energy quantities while generating waste streams. Steel production requires coal for smelting. Aluminum smelting demands intensive electricity. Cement manufacturing releases carbon through chemical reactions plus fuel consumption. Plastic production relies on petroleum derivatives while creating persistent pollution. Transportation networks connect global commerce yet generate substantial emissions. Shipping moves goods across oceans using heavy fuel oil. Trucking distributes products overland using diesel fuel. Aviation enables rapid travel while burning jet fuel at high altitudes where emissions prove particularly warming. Digital infrastructure, seemingly clean, operates through massive energy consumption. Data centers cooling servers consume electricity continuously. Cryptocurrency mining demands computational power requiring vast electrical inputs. Smartphone manufacturing involves rare earth mining with significant environmental consequences. Agriculture mechanization increased productivity, while creating dependencies on fossil-fueled machinery, synthetic fertilizers, and pesticide applications. Modern farming feeds billions yet contributes emissions through equipment operation, chemical production, and land use modifications. Some emissions occur directly, while others emerge from supporting infrastructure systems. Concrete for roadways, steel for automobiles, plastics for containers all contribute. Transportation alone generates substantial emission portions. Private automobiles, cargo trucks, maritime vessels, and aircraft depend heavily on petroleum products. Electric automobile numbers increase, yet transformation remains incomplete. Aviation and maritime sectors resist large-scale electrification. Supply networks delivering merchandise to residences and enterprises operate on fossil energy foundations. Manufacturing contributes differently. Cement creation releases carbon dioxide through chemical reactions converting limestone into lime. Steel manufacturing demands extreme temperatures, typically coal-provided. These operations underpin global infrastructure, bridges, structures, power transmission, harbors. Alternatives emerge but remain costly or developmentally early. Technology transformed agriculture through tractors, irrigation networks, synthetic nutrients, and pesticides, boosting productivity while feeding billions. However, these innovations increased emissions, degraded soil quality, and contributed to water contamination. Fertilizer application releases nitrous oxide, a powerful greenhouse gas. Equipment operates on fuel. Agricultural territory clearance, particularly in tropical areas, drives deforestation, eliminating carbon absorption capacity. Simultaneously, technology enabled extensive cooling systems, air conditioning, refrigeration, data centers, requiring energy while utilizing refrigerants with substantial warming potential. These innovations improve health, safety, and convenience, while creating additional electrical grid pressure, especially in warmer climates where cooling becomes necessity rather than luxury. Digital technology presents unique complications. Daily devices, smartphones, laptops, rotors require rare earth metals, extracted through energy-intensive mining processes carrying environmental and social consequences. Data storage and cloud computing, invisible to users, depend on server facilities consuming enormous electricity quantities. Digital infrastructure expansion amplifies environmental impact. Waste extends beyond emissions to physical byproducts, electronic waste from discarded devices, plastic from packaging and production, chemical discharge from industrial operations. These materials accumulate in landfills, waterways, and marine environments. Many persist without easy decomposition, some proving toxic to ecosystems and humans. Despite challenges, technology provides tools addressing problems it helped generate. Renewable energy expands rapidly. Wind, solar, and hydroelectric sources supply clean electricity at previously unrealistic scales. Battery storage improves. Smart electrical networks balance supply and demand. Electric automobiles become more efficient while charging infrastructure expands. Energy efficiency innovations emerge from superior insulation and lighting to enhanced industrial operations. Often, energy conservation reduces costs, accelerating adoption. Buildings receive designs using less heating and cooling. Appliances gain efficiency. Cities employ data managing traffic, reducing waste, and optimizing public transportation. Carbon capture technologies develop removing atmospheric carbon dioxide or power facility exhaust. Some employ chemical scrubbing, while others utilize enhanced mineral weathering or biological approaches. These expensive systems lack widespread deployment but could contribute to net zero emission goals, especially for challenging decarbonization sectors. Technology assists tracking and modeling environmental transformation. Satellites observe deforestation, ice melting, and water level increases. Sensors gather air and water quality data. Machine learning algorithms analyze patterns and improve predictions. This information helps governments, enterprises, and communities plan effectively. Early warning systems for storms benefit communities. Agricultural precision techniques reduce water and fertilizer consumption. Drones monitor crop conditions. Automated irrigation responds to real-time circumstances. Vertical farms and laboratory-grown meat offer food production models with reduced footprints. While not universally accessible, these tools indicate more efficient and sustainable systems. Construction evolves through new materials like low-carbon cement, engineered timber, and recycled steel entering markets. Three-dimensional printing explores waste reduction in building. Modular designs enable easier upgrades and repurposing. Retrofitting existing structures for energy efficiency often costs less than replacement while avoiding new construction emissions. Despite advances, technology alone cannot resolve problems. Many emissions stem not from machine construction or power sources, but from usage demands driving frequency, consumption levels, waste generation. Addressing this requires behavioral, systemic, and expectational changes. Trade-offs exist. Lithium, cobalt, and battery material mining can damage ecosystems while creating new dependencies. Solar panels and wind generators require territory, raw materials, and long-term disposal planning. Constructing clean energy infrastructure meeting climate objectives demands coordination, investment, and careful strategy. Access remains uneven. Wealthier nations afford faster new technology deployment. The poorer regions, often experiencing worst climate impacts, may lack transition resources. Bridging disparities connects to broader climate justice conversations, ensuring solutions become available and fairly distributed. Technology always mirrors human priorities, reflecting values, fears, and preservation hopes. Careless usage multiplies problems, yet thoughtful application enables restoration, not replacing nature but aligning with it through efficiency, circular design, renewable power, and closed-loop systems, reshaping progress concepts. This brings us to another story aspect. Despite machinery and knowledge, we're not the sole planetary force. Sometimes threats originate beyond Earth from deep space, solar activity, or cosmic events without warning or preference. We examine these quiet, distant hazards rarely considered but shaping Earth's history and potentially returning. Amid Earthly urgency, warming contamination, habitat destruction, our planet exists within a vastly larger system. Space isn't empty but filled with motion, radiation, debris, and events operating beyond human control. Earth represents a small moving target within an active, sometimes volatile solar system. Usually space ignores us, but not always. Solar activity fluctuates dramatically. Our star experiences cycles generating increased radiation, magnetic storms, and particle streams affecting satellite operations, communication networks, and electrical grids. Extreme solar events could disable technology supporting modern civilization. Asteroid impact shaped planetary history. While catastrophic collisions remain rare, smaller objects regularly enter our atmosphere. Most burn up harmlessly, yet larger specimens could devastate regions or trigger global climate disruption. Detection and deflection systems develop slowly against these cosmic projectiles. Gamma-ray bursts from distant stellar explosions could sterilize planetary surfaces within their radiation cones. These events, while improbable, demonstrate universe-scale forces dwarfing terrestrial concerns. Supervolcanic eruptions represent another threat, bridging terrestrial and cosmic scales. Yellowstone, Toba, and similar systems could inject massive ash quantities into the atmosphere, blocking sunlight and triggering volcanic winters lasting years. Magnetic field reversals occur periodically, potentially exposing Earth's surface to increased cosmic radiation during transition periods. While life survived previous reversals, technological civilization's vulnerability to radiation remains untested. Climate change interacts with these cosmic factors in unpredictable ways. Weakened ecosystems show reduced resilience against additional stresses. Technological dependencies create new vulnerabilities. Understanding these connections helps prepare for compound threats requiring both mitigation and adaptation strategies. Approximately 66 million years passed, a massive asteroid collided with present-day Yucatan Peninsula territory. This impact generated enormous blazes, tsunamis, and atmospheric modifications, blocking solar radiation for months. That singular occurrence widely caused dinosaur extinction alongside roughly 3/4 of contemporary Earth species. The event proved sudden, worldwide, and permanent, a cosmic restart. Currently, asteroid knowledge exceeds previous understanding. Thousands receive cataloging and tracking. Most reside within the asteroid belts separating Mars and Jupiter, yet some, designated near-Earth objects, follow orbital paths approaching our world. NASA plus additional space organizations continuously monitor these bodies, seeking anything sufficiently large causing damage should it intersect Earth's trajectory. Positive news: annual large impact risk remains minimal. Negative news: risk isn't zero. Smaller asteroids, those potentially devastating cities rather than destroying continents, occur more frequently. Atmospheric entry burns many before ground contact, yet not all. During 2013, a 20-meter-wide meteor exploded above Chelyabinsk, Russia, with several hundred kiloton TNT equivalent force. The resulting shockwave injured over 1,000 individuals and damaged structures across extensive areas, a near miss by cosmic measurements. Impact prevention efforts advance. Missions like NASA's DART successfully modified small asteroid trajectories through collision, demonstrating that sufficient warning enables dangerous object deflection. Detection remains crucial. Earlier identification improves disaster avoidance possibilities. Space monitoring systems matter despite rarely generating headlines. Asteroids aren't solitary cosmic hazards. Our life-sustaining star isn't entirely harmless. It emits continuous charged particle streams, solar wind, and occasionally releases substantial energy bursts called solar flares and coronal mass ejections. These phenomena interfere with satellites, radio communications, navigation equipment, and electrical networks. Most remain minor, yet significant solar storms occurred historically. The famous Carrington event during 1859 caused worldwide telegraph system failures. Wire sparks flew while auroras illuminated night skies reaching Caribbean latitudes. Similar storms today could disrupt continental power supplies, communication networks, and internet infrastructure. Some satellites might become disabled. Aircraft could face grounding. Financial systems and data facilities might experience cascading breakdowns. Space weather forecasting exists, resembling terrestrial weather prediction. However, solar activity prediction remains challenging. Sunspot observation and flare intensity measurement occur, yet major solar storm timing and magnitude remain uncertain. Ongoing infrastructure hardening against such events continues, though many systems stay vulnerable. The Sun, despite consistency, retains sudden change capacity. Beyond asteroids and solar disturbances exist rarer phenomena: gamma-ray bursts, nearby supernovas, cosmic ray shifts theoretically affecting Earth's atmosphere or climate. Most remain speculative or temporally and spatially distant. Their probabilities stay low while impacts depend on proximity and scale, yet they remind us Earth's stability isn't entirely self-contained. Space debris presents ongoing concerns: satellite, rocket, and human-made object fragments orbiting Earth. Increasing device launches elevate collision risks. Collisions generate additional debris, potentially damaging other satellites or space stations. While not directly threatening Earth's habitability, this could affect monitoring and communication capabilities critical for managing various risks. Looking outward, some perceive space-based hope, exploration, expansion, or escape opportunities. Space agencies and private enterprises develop lunar base plans, Mars expeditions, and asteroid mining projects. These initiatives represent progress, insurance, or frontier advancement. Yet currently, no extraterrestrial location provides complete long-term human survival conditions. Off-planet existence would require artificial systems, controlled environments, constant supply chains, and flawless engineering. Single-system failures would prove far less forgiving than manageable Earth-based failures. This doesn't negate continued space exploration value. Understanding other worlds enhances self-knowledge. Satellites enable weather study, deforestation tracking, ice loss measurement, and pollution monitoring. Telescopes facilitate deeper space and time observation, expanding universal knowledge. Mars, Venus, and outer planet missions provide climate, geological, and life boundary insights. However, space fascination doesn't solve climate change, biodiversity loss, or ecosystem collapse. Earth remains our only known complex life-supporting location, not merely through technology but naturally balanced air, water, soil, and light systems. Exploration cannot change our planetary adaptation, shaping, and rhythmic connections. Space psychology effects include astronaut-described overview effects, profound Earth orbital viewing realizations, revealing smallness, fragility, and interconnectedness. No borders or divisions exist, just blue-white spheres floating in darkness. Perspective shifts influence science, art, philosophy, and global cooperation. Distance sometimes reveals value. Cosmic threats may seem remote yet contextualize Earth. This molten core, thin atmosphere, flowing water, steady orbit planet represents rare, finely tuned conditions. Creative forces, collisions, cooling, chemical reactions, biological evolution could easily have produced less hospitable environments. Nevertheless, stability persists temporarily. Space-based risks, though genuine, largely exceed our influence. As we control Earth-boundary living, constructed machinery, harvested forests, burned energy, protected species. These represent our decisions shaping whether this location remains secure, predictable, and supportive of dependent life. Climate change conversations often focus on distant futures, abstract statistics, or technological solutions. Yet the story remains fundamentally about home, this singular planet supporting everything we know and cherish. Every temperature degree, emission reduction, protect ecosystem, and sustainable choice contributes to maintaining habitability. Time remains available, though not unlimited. Scientific understanding grows. Renewable technologies advance. Conservation efforts expand. International cooperation increases, albeit slowly. Young generations demonstrate environmental awareness and activism exceeding previous levels. Innovation accelerates across multiple sectors simultaneously. However, transformation requires unprecedented speed and scale. Individual actions matter yet prove insufficient without systemic changes. Governments must implement policies. Corporations must modify operations. Communities must adapt practices. International agreements must strengthen and receive enforcement. The challenge extends beyond emission reductions to comprehensive sustainability, protecting biodiversity, restoring damaged ecosystems, ensuring equitable resource distribution, and building resilient communities. Success demands recognizing interconnectedness, climate, nature, technology, society, and space as components within unified systems. Future generations deserve inheriting a world maintaining natural beauty, supporting diverse life, and providing opportunities for prosperity and fulfillment. This inheritance depends on current decisions and actions. The cosmic perspective reminds us of Earth's preciousness and fragility, while emphasizing our responsibility as temporary stewards. Looking towards stars doesn't diminish earthly importance, but amplifies it. In vast universe darkness, Earth shines as extraordinary sanctuary deserving protection, respect, and careful management. Our survival and thriving depend not on escaping this world, but on learning to live harmoniously within its boundaries, while preserving its capacity to sustain all life forms calling it home. The story continues, and its conclusion remains unwritten. The heavens can still astonish us, yet Earth proves equally surprising, particularly when pushed beyond sustainable limits. Our narrative now descends toward boundaries we're approaching, depleting resources, and questions about growth continuation within finite systems. Solar radiation provides Earth's warmth, illumination, and energy, powering everything from vegetation to weather patterns to metropolitan areas. Each dawn initiates fresh cycles while dusk brings temporary closure, rhythms so dependable we seldom contemplate solar nature or longevity. However, stars possess lifespans like planets, and even our most dependable celestial source will eventually transform. Our star represents middle-aged stellar development, approximately 4.6 billion years old. Nuclear fusion powers it, hydrogen converting to helium within its core. This reaction releases tremendous energy pushing outward, balancing gravitational inward pull. Maintaining this equilibrium keeps solar stability, not perfectly steady with cycles and flares, yet generally dependable. Eventually, fuel depletion occurs, not imminently. Roughly 5 billion years remain before core hydrogen exhaustion prevents current burning patterns. When transformation begins, changes start gradually, then become dramatic. Expansion, increased brightness, and instability follow, not sudden flashes but staged progressions. Currently, solar luminosity slowly increases. Astronomical estimates indicate past few 100 million years witnessed approximately 10% brightness enhancement. Coming billion years continue this trend. Earth's temperature will gradually climb without greenhouse gas assistance. Eventually, oceanic evaporation begins, water vapor increases, and planetary climate shifts beyond current life survival capabilities. This differs from human-influenced climate change. We cannot affect it, nor will it occur within any contemporary planning or crisis timeframes. Understanding remains valuable because it contextualizes Earth within longer narratives where even stable systems possess endpoints. Aging cores contract while outer layers expand. Red giant development grows sufficiently large, potentially engulfing Mercury and Venus. Earth's consumption remains uncertain. Some models suggest survival, barely, even escaping solar surface contact. Conditions become unrecognizable. Atmosphere stripped, surface scorched, crust possibly melted. By then, terrestrial life disappears unless transported spaceward or transformed beyond current imagination. Biosphere dependency on narrow temperature, pressure, and chemical ranges fails as solar evolution disrupts balance. Following red giant phases, outer layer shedding creates white dwarf remnants, dense, hot formations, Earth-sized yet containing half solar mass. Fusion energy production ceases, leaving slow cooling across trillions of years, eventually fading into darkness. Earth, if existing, becomes quiet, frozen rock orbiting faint illumination. This pattern isn't unique, standard life cycle for sun-sized stars. Larger stars burn faster, dying violently through supernova explosions, scattering heavy elements spaceward. These explosions actually forged elements within your body: bone calcium, blood iron, cellular carbon, all crafted in earlier stars predating Earth's existence. Long-term perspective reshapes habitability thinking. Earth isn't permanently secure, having survived mass extinctions, deep freezes, volcanic winters, asteroid impacts, and climate oscillations, eventually facing conclusion far exceeding human-driven challenges. This doesn't diminish current urgency but adds contextual layers, reminders that without us, time continues ticking. Knowledge also transforms planetary thinking. Mars once contained liquid water. Venus may have experienced temperate climates before atmospheric thickening. Solar brightening pushed these worlds past key thresholds, eliminating life-supporting conditions. Earth occupies narrow windows, balance zones temporary by nature. Questions arise about human construction fate. Our disappearance wouldn't immediately eliminate satellites, probes, rovers, and stations, silent machinery gradually deteriorating in space, cold or re-entry heat. Earth's surface would eventually erode civilization signs through forest, ocean, and weather reclamation of concrete and steel, speed depending on system survival. Life forms adapting or evolving to survive, coming hundreds of millions of years, face solar brightening as final boundaries. Unless discovering Earth departure methods or planetary controls through relocation, concepts currently belonging more to science fiction than established science, such life confronts uninhabitable futures regardless of advancement. Time vastness complicates certain questions. Billion-year spans exceed human brain design for visualization. Immediate importance focuses on coming decades, story portions we still influence. Solar eventual death highlights even permanent things' temporariness. This doesn't render effort meaningless but increases meaning. We inhabit brief moments when Earth remains habitable, atmosphere stable, and humans capable of understanding both limitations and reach. These moments won't persist forever but belong to us now. Returning to present scale, we examine daily choices, dependent systems, and limits, originating not from stars but from finite world resources. Earth appears solid, fixed, stable, spinning positioned correctly, tilted appropriately, moving predictably around our star. For most daily purposes, accuracy exists. Ground remains beneath feet. Seasons follow familiar patterns. Day length stays relatively constant. Over extended timescales, Earth doesn't maintain stillness. It shifts, tilts, wobbles slowly, silently, with genuine consequences. These modifications are Milankovitch cycles, named after Serbian scientist Milutin Milankovic, studying how orbital and rotational variations influence climate across millennia. Three primary cycles exist: eccentricity, obliquity, precession. Each alters sunlight quantities reaching different planetary regions and energy distribution across seasons and latitudes. Eccentricity describes Earth's orbital shape around the Sun, not perfect circles but slightly stretched ellipses. Approximately 100,000-year cycles create more or less elliptical orbits. Circular orbits maintain roughly consistent solar distances yearly. Elliptical variations increase seasonal distance differences, affecting seasonal intensity, especially hemisphere-specific impacts. Obliquity represents Earth's axial tilt, angles between rotational axes and orbital planes. Current tilt approximates 23.5 degrees, creating seasonal variations. Orbital positioning tilts different hemispheres toward or away from solar radiation, generating sunlight variations. However, tilt isn't fixed, wobbling between roughly 22 and 24.5 degrees across 41,000-year cycles. Higher tilts create extreme seasons. Lower tilts produce milder variations. Precession involves slow axial wobbling, resembling spinning top motion. This 26,000-year cycle gradually shifts axis orientation relative to orbital positioning, changing seasonal timing. Northern Hemisphere summers could occur during maximum solar distance instead of minimum proximity, altering seasonal strength and timing. Cycles don't operate independently, but combine complexly without immediate influence. They shift solar energy distribution slowly, interacting with oceanic currents, ice formations, greenhouse gases, and vegetation. Effects require millennia for unfolding, yet can trigger major transformations including ice age advancement and retreat. Recent millions of years witnessed glacial and interglacial patterns. Roughly every 100,000 years, ice sheets expanded across North America, Europe, Asia, then melted back. Sea levels dropped and rose. Ecosystems migrated and reformed. Ecosystems migrated and reformed. These shifts resulted partly from Milankovitch cycles, amplified by feedback mechanisms like albedo, ice and snow reflectivity, and atmospheric carbon dioxide concentrations. We currently inhabit an interglacial period called the Holocene, beginning approximately 11,700 years ago. Unusual stability supported agriculture, urban development, and modern civilization emergence. However, human emissions have disrupted this natural trajectory. Atmospheric carbon dioxide and additional greenhouse gas concentrations now surpass anything witnessed during previous interglacial periods. This means climate's natural rhythm, the gradual choreography of wobbles and tilts, faces override by much swifter transformations. Climate warming occurs far more rapidly than orbital changes alone could generate. Even if cooling phases were scheduled, greenhouse gases have pushed systems in opposite directions. Nevertheless, underlying cycles persist. Earth's orbital patterns continue shifting. Axial tilting continues changing. Precession continues nudging seasonal calendars. These modifications may regain relevance across longer timescales spanning tens of thousands of years. Currently, however, climate's dominant force isn't orbital mechanics but human activity. These cycles aren't Earth's only movements. Axis positioning shifts slightly annually due to planetary mass distribution changes. Melting ice, groundwater depletion, and large-scale air and water movements alter spinning patterns. These shifts prove minuscule, often measured in milliseconds, yet remain detectable through modern instruments. Over time, they affect daily duration by milliseconds. True polar wander represents another phenomenon involving entire solid Earth reorientation relative to rotational axes. Unlike precession, this process moves much slower, demonstrating that even large-scale planetary structures aren't entirely fixed. Geological records suggest true polar wander occurred previously, likely linked to Earth's internal dynamic changes. Subtle shifts carry practical effects. Satellite positioning, GPS systems, and astronomical calculations depend on knowing Earth's exact orientation. Climate models factor orbital parameters for understanding past and future conditions. Better understanding these slow movements improves separation of natural trends from human-driven ones. This reveals Earth's habitability always depended on delicate balance, not merely atmospheric chemistry but sunlight delivery to surfaces. Small shifts, when amplified by feedbacks, create major changes. Ice sheets don't respond instantly, yet once growth or melting begins, momentum carries through millennia. These cycles highlight Earth's climate always changed. Current differences involve pace. Natural changes unfold across thousands to millions of years. Present warming happens within decades. Speed differences prove critical, because ecosystems, agriculture, and infrastructure rely on stability. When conditions change faster than adaptive systems allow, disruption risks increase. Importantly, while we cannot control Earth's orbital variations, we can choose responses to current changes. Axis tilting and orbital shapes remain beyond influence, yet emissions, land use, and energy choices stay within reach. Some people reference these cycles for downplaying human climate influence, arguing warming might be natural. Data doesn't support this position. Climate models, including only orbital changes, don't explain recent trends. Only when greenhouse gases are included do patterns match observations. Natural rhythms persist but become drowned by stronger signals. Therefore, Earth continues spinning, slowly wobbling on its axis, orbiting an evolving star. Cycles continue shaping long-term patterns previously dominant, but now part of larger pictures where human choices became the most immediate planetary change sources. Planetary motion remains subtle, slow, nearly invisible daily. Over time, however, effects accumulate, like water, air, and ice movement. It reminds us that seemingly stable things stay in perpetual motion. Ice might appear life's opposite, cold, motionless, silent. Yet it represents one of Earth's most informative materials. Locked within glaciers and ice sheets are climate records, ancient atmospheric conditions, shifting temperatures, and planetary long-term memory. When scientists seek understanding of Earth's system behavior before satellites, thermometers, or written history, they frequently turn to ice. Glaciers form where annual snowfall accumulates, compacting under its weight into dense crystalline layers. Over time, layered ice flows slowly downhill, shaped by gravity and topography. In locations like Greenland and Antarctica, these flows stretch across entire continents, forming kilometer-thick ice sheets. Each layer captures atmospheric traces from formation periods. Tiny air bubbles, dust, volcanic ash, pollen, and oxygen and hydrogen isotopes reflect temperature conditions. Drilling deep into these layers enables scientists to reconstruct climate records spanning hundreds of thousands of years. Oldest ice cores provide atmospheric snapshots extending beyond 800,000 years. They reveal repeating patterns, glacial periods with expanded ice sheets and dropped sea levels, followed by warmer interglacials like our current period. These shifts were often gradual, tied to orbital changes and reinforced by feedbacks. Ice's clearest signals show connections between carbon dioxide and temperature. During glacial periods, CO2 levels stayed low. During warm periods, they increased. Cause and effect operate bidirectionally. Warming releases carbon while carbon drives additional warming. It's a feedback loop, not linear progression, yet patterns remain consistent. When CO2 rises quickly, temperatures follow. Ice also demonstrates current carbon dioxide levels far exceed natural ranges for recent several 100,000 years. Since Industrial Revolution, atmospheric CO2 increased over 50%, reaching levels unseen for at least 3 million years. Increase rates surpass anything found in ice core records. Speed matters because it provides natural systems less adjustment time. As planetary warming occurs, glaciers and ice sheets respond. Mountain glaciers worldwide retreat from Alps to Andes, Alaska to Himalayas. Many cases show visible changes within single human lifetimes. Some smaller glaciers disappeared completely. These losses affect more than scenery. Glaciers store water supporting agriculture, drinking supplies, and downstream river systems. Shrinkage changes seasonal water flows. At polar regions, scale expands dramatically. Greenland's ice sheet contains sufficient water raising sea levels approximately 7 meters if fully melted. Antarctica holds much more, enough elevating sea levels over 50 meters. While these outcomes aren't expected immediately, transformation direction already began. Both ice sheets lose mass. Some portions thin while others accelerate as ice slides more rapidly towards seas. Surface melting doesn't solely drive this process. Many locations experience warm ocean water flowing beneath ice shelves, floating glacier extensions helping restrain flow. When ice shelves thin or collapse, glaciers behind them accelerate. This occurs in West Antarctica and Greenland portions. The processes prove uneven, yet once begun, stopping becomes difficult. Some ice systems may already follow paths toward long-term retreat, even if warming slows. These processes involve feedback loops. Melting ice exposes darker underlying land or water. These surfaces absorb more sunlight than ice, accelerating local warming, the albedo effect, another reinforcing Arctic cycle causing especially rapid changes. Summer sea ice declined dramatically across recent decades. Reduced ice means increased heat absorption, leading to less ice the following year. Permafrost frozen polar soil holds vast carbon amounts as decayed plant material never fully decomposing. Ground thawing activates microbes beginning organic matter breakdown, releasing atmospheric carbon dioxide and methane. Methane proves particularly potent as greenhouse gas. This process remains slow and patchy, yet adds another climate system feedback loop. Ice doesn't merely reflect changes, it amplifies them while recording them. Ice cores revealed evidence of past volcanic eruptions, massive wildfires, and atmospheric composition shifts. They've confirmed recent warming's unusual pace and scale, serving as long-term context for current changes, not predictions but comparisons. Sea level elevation isn't uniform, varying based on oceanic currents, gravitational modifications, and local territorial movement. However, trends remain consistent. Global averages climb while pace accelerates. This impacts coastal municipalities, island territories, estuaries, and wetlands. Saltwater infiltration affects groundwater systems, flooding frequency increases, infrastructure designed for 20th century conditions struggles maintaining effectiveness. Adaptation proves possible through protective barriers, zoning modifications, and wetland rehabilitation. Success requires planning, resources, and long-term vision. Ice narratives intersect with geopolitics. Arctic sea ice retreat opens new shipping corridors while making petroleum and gas reserves more accessible. Nations invest in Arctic military installations, harbors, and research facilities, creating tensions in previously inaccessible regions. Climate change affects not merely ecosystems but national strategic interests. For indigenous polar communities, ice loss transcends environmental concerns. It disrupts culture, traditions, and livelihoods. Hunting patterns transform. Travel becomes hazardous. Sacred locations vanish. Knowledge systems evolved through ice partnerships face unprecedented testing. Many communities adapt by combining traditional wisdom with contemporary tools, yet transformation pace proves rapid. Even distant from glaciers, ice loss creates ripple effects. Arctic sea ice changes affect jet streams and weather patterns across northern hemispheres. Some researchers link reduced ice coverage to more persistent weather systems, extended heat waves, stalled storms, colder winters in certain areas. These connections require continued study, yet links between polar changes and global patterns grow clearer. Time remains for avoiding worst outcomes. Ice sheets don't melt overnight. Aggressive emission reductions and intelligent adaptation could slow or stabilize some retreat. Feedback loops can be softened, though certain threshold crossings become irreversible. Ice often functions as warning systems, slow initial change, yet difficult stopping once movement begins. Therefore, ice transcends frozen water. Its climate archives, feedback mechanisms, geographic forces, and signals, while movement indicates planetary system shifts. Melting marks turning points. Disappearance removes not only mass but memory. Cities often symbolize progress, locations where technology, culture, economy, and infrastructure converge. They're dense, active, filled with systems supporting modern existence. Yet they reveal how human activity concentrates energy, heat, and impact with outward ripple effects. In worlds facing rising temperatures and shifting climates, cities become simultaneously more important and vulnerable. Over half the global population inhabits urban areas. Numbers are expected growing, especially across Asia and Africa, where cities expand rapidly. Urbanization brings opportunities, service access, employment, education, healthcare, while creating pressure. Land receives paving. Trees face removal, buildings rise. Vehicles crowd streets. Each component adds environmental load. Urban heat island phenomena represent clearest effects. Cities tend warming beyond surrounding rural territories, often by several degrees, particularly nightly. Reasoning appears simple. Dark surfaces like asphalt and concrete absorb daytime heat, releasing it slowly at night. Rural areas feature vegetation helping air cooling through evaporation and shading. Cities often lack or diminish these cooling systems. Extra heat carries genuine effects, increasing air conditioning demand, adding power grid stress, and potentially increasing emissions in less clean energy power systems. It raises heat-related illness risks, especially for vulnerable populations, elderly individuals, outdoor workers, and people lacking cooling access. Extreme cases witness urban heat waves causing mortality spikes. Urban heat distribution isn't uniform. Wealthier neighborhoods often feature more trees, superior insulation, and cooling access. Poorer areas may lack green spaces, possess older infrastructure, and receive less heat emergency support. This creates environmental inequality, where climate change risks amplify through local conditions. City design either softens or worsens effects. Materials matter. Lighter colored surfaces reflect more sunlight. Vegetation helps cooling air and managing stormwater. Green roofs, tree canopies, and parks reduce temperature spikes. Water features add humidity and cooling potential. Transit systems reduce automobile reliance, lowering engine and tailpipe heat. Every design choice accumulates. Noise represents another urban life feature often unnoticed. IDs fill with sounds, engines, sirens, construction, voices, machinery. Constant noise over time affects sleep, stress levels, cardiovascular health, and mental well-being. It also influences wildlife. Birds may alter calls in noisy areas or avoid them entirely. Insects, mammals, and urban waterway aquatic species respond to human soundscapes. Light provides the third layer, bright, constant, and expanding, Office towers to street lamps to billboards make cities shine nightly. Light enhances street safety and enables after-dark activity while interfering with natural rhythms. Human bodies respond to light cues regulating sleep, hormones, and alertness. Constant artificial night light exposure disrupts these patterns, causing fatigue, metabolic issues, and reduced sleep quality. Wildlife responds similarly. Many animals depend on darkness for feeding, migrating, or reproducing. Artificial light disorients birds, turtles, insects, and other species, changing predator-prey dynamics, altering reproductive timing, and fragmenting habitats. Even prolonged lighting exposure may shift plant growth cycles. Over time, night becomes less boundary and more diluted daytime. Light pollution reduction methods exist: shielded fixtures, warmer color temperatures, dimming schedules, and thoughtful placement. Some cities begin adjusting lighting strategies for human health and ecosystem protection. Many locations maintain washed-out night skies with few visible stars where thousands should appear. City environmental footprints extend beyond boundaries. They depend on resources gathered elsewhere: rural food, distant water sources, regional grid energy, global supply chain materials. Urban-produced waste often exports to landfills, oceans, or incinerators, affecting communities far from origins. Urban centers produce substantial global emission shares. Buildings require heating and cooling, cars and trucks burn fuel. Industry and infrastructure consume power, yet cities also concentrate solutions. Transit systems, dense housing, energy-efficient buildings, and shared resources offer per capita impact reduction methods. Well-planned urban living can prove more sustainable than suburban sprawl or dispersed development. Adapting cities to changing climates means addressing multiple simultaneous risks: heat, flooding, storm surges, drought, air quality, and social vulnerability. This requires upgrading infrastructure built for different climates: pipes, bridges, roads, electrical systems, while housing growing populations, supporting economies, and maintaining services. Some cities already take action. Urban planners integrate green infrastructure: bioswales, rain gardens, permeable pavement managing stormwater and reducing flooding. Others build cooling centers, plant urban forests, and revise building codes for energy efficiency. Some invest in resilient transit, renewable energy, and microgrids operating independently during outages. Community involvement proves essential. Climate adaptation isn't merely technical challenges, it's social. Residents understand neighborhoods, local needs, and histories. Including them in planning creates better outcomes, increased trust, and more equitable solutions. Grassroots efforts from community gardens to cooling campaigns often move faster than top-down programs. Technology plays roles through sensors measuring temperature, air quality, and noise real-time. Data helps target interventions where most needed. Digital tools support smart grid management, real-time transit updates, and citizen problem reporting. Technology functions as tools, not independent solutions, working best when combined with strong governance, good design, and public engagement. Resource equality among cities varies significantly. Wealthier locations invest in adaptation, while poorer cities struggle with basic infrastructure before adding climate stress. International support, knowledge sharing, and flexible financing models are needed closing gaps. Climate resilience shouldn't be luxury, it should be standard. Cities shape culture, behavior, and norms. People's movement, eating, cooling, and nature interaction patterns receive urban environment influence, making cities powerful change locations. Safe cycling increases participation. Efficient buildings reduce energy use. Green neighborhoods decrease heat stress. Dark skies might encourage stargazing. Urban areas aren't separate from nature, they're part of it. They occupy land previously forested, prairie, or wetland. Rain continues falling. Rivers keep flowing. Wildlife still passes through. Recognizing connections and designing accordingly makes cities not merely more livable but more resilient. The challenge ahead isn't whether cities will change, but how expanding with more asphalt, emissions, and fragmentation, or growing reflecting limits, adapting to risks, and creating new balance forms. We rarely consider air, invisible, weightless in perception, constantly surrounding us. Every single moment your body performs an action more critical than your heartbeat, more essential than blinking, more vital than any thought crossing your mind. 20,000 times each day, your lungs pull in the substance that separates existence from extinction. Yet this life-sustaining force remains completely invisible, utterly taken for granted until something goes terribly wrong. Right now, as you absorb these words, that precious resource surrounding you might already be changing in ways that could reshape human survival forever. The atmosphere wrapping our planet operates like an incredibly delicate bubble, extending merely 100 kilometers from ground level to the void of space. However, the breathable portion exists within just the first 10 kilometers, a razor-thin layer called the troposphere. This gossamer shell contains everything necessary for breathing: 78% nitrogen, 21% oxygen, plus minute quantities of argon, carbon dioxide, water vapor, and various trace elements. Throughout the epochs when complex organisms developed, this precise mixture remained remarkably consistent, stable enough to nurture lungs, gills, leaves, and countless ecological networks. Oxygen serves as the cornerstone of animal existence. Insufficient amounts prevent cellular function entirely. Excessive levels become poisonous, destroying tissues while dramatically increasing fire hazards. Earth's atmospheric balance wasn't always this perfect. During our planet's infancy, oxygen existed in virtually negligible amounts. Billions of years passed before photosynthetic microorganisms gradually elevated concentrations to breathable standards. This transformation, called the Great Oxidation Event, unfolded slowly, chaotically, yet fundamentally altered everything. While enabling complex organisms to emerge, this same process triggered one of our planet's earliest mass extinctions, eliminating countless species unable to adapt to the revolutionary chemistry. Contemporary oxygen concentrations appear relatively steady, though permanence remains an illusion. Should carbon emissions persist in driving planetary warming, while simultaneously depleting oceanic oxygen reserves, atmospheric oxygen might decline slightly across centuries or millennia. While not reaching levels making breathing impossible, such reductions could impact human health, agricultural productivity, and fire behavior patterns. Though not representing an immediate threat, these possibilities remind us that even seemingly stable atmospheric components can shift under sustained pressure. More pressing concerns involve contaminated environments. Throughout urban centers and industrial regions worldwide, toxic substances regularly make breathing hazardous. These pollutants encompass particulate matter, including PM2.5 and PM10, nitrogen dioxide, sulfur dioxide, ground-level ozone, plus volatile organic compounds. Sources include automobiles, manufacturing facilities, power generation plants, biomass burning, and construction activities. Once inhaled, these contaminants penetrate lungs, enter bloodstreams, and can even reach brain tissue. Environmental contamination contributes to millions of preventable deaths annually. It elevates risks for cardiovascular disease, respiratory ailments, strokes, and specific cancer types. Children, elderly individuals, and those with existing medical conditions face particular vulnerability. Brief exposure episodes can trigger asthma episodes or extreme fatigue. Prolonged contact reduces lifespan expectations while impairing cognitive development. Certain regions experience such severe conditions that residents wear protective masks daily, long before global pandemics normalize this practice. Contamination distribution follows deeply unfair patterns. Lower-income communities and marginalized populations frequently reside near industrial zones, major highways, and polluting installations. This creates compounded hardship where social inequality meets environmental hazards. While initiatives promoting cleaner energy sources, vehicle restrictions, and mass transit systems offer multiple advantages, implementation requires political commitment, financial investment, and rigorous enforcement. Wildfire events have emerged as another source of unbreathable conditions. As forests become increasingly arid and burn more frequently, smoke travels hundreds or thousands of kilometers, shrouding entire regions in dangerous haze. Fine particles within wildfire smoke prove especially threatening, penetrating deep into lung tissue and crossing into circulatory systems. These incidents occur episodically, but with growing frequency across locations like California, Australia, and southern Europe. Ground-level ozone formation occurs when sunlight interacts with pollutants such as nitrogen oxides and volatile organic substances, creating additional health concerns. This differs from beneficial stratospheric ozone that shields against ultraviolet radiation. This harmful variant irritates respiratory passages and diminishes lung capacity. Ozone concentrations typically surge during hot weather periods, intensifying the combined effects of heat waves and contamination. Certain global regions experience sand and dust storm phenomena that compound breathing difficulties. As soils become desiccated and vegetation coverage shrinks, winds lift microscopic particles into the atmosphere. While common in desert territories, land degradation and climate shifts are expanding their geographic reach. Dust affects respiratory wellness, blocks sunlight, and can transport bacteria or fungi across vast distances. Indoor environments present often overlooked challenges. People spend substantial portions of their lives inside homes, workplaces, or transportation vehicles. Indoor conditions are influenced by cooking activities, cleaning chemicals, construction materials, and ventilation systems. Within poorly ventilated spaces, harmful substances accumulate, particularly in energy-efficient buildings designed with tight seals. Mold, radon gas, carbon monoxide, and chemical vapors represent common indoor hazards. Solutions involve improved filtration systems, fresh circulation networks, and careful material selection, though public awareness remains surprisingly limited. Elevation factors also affect breathing capacity. At higher altitudes, atmospheric pressure decreases while oxygen becomes thinner. Human physiology can adapt to certain extents, but beyond approximately 8,000 meters, the notorious death zone ME, even acclimatized mountaineers cannot survive extended periods without supplemental oxygen. This reality demonstrates that breathable conditions depend not solely on chemical composition, but also pressure and delivery mechanisms. Should Earth's climate or atmospheric pressure undergo dramatic transformations, breathing capacity would cease being guaranteed. Geoengineering concepts such as solar radiation management or carbon capture technologies could potentially, if implemented carelessly, modify atmospheric chemistry. Most theoretical models aim to prevent harmful side effects, yet uncertainties persist. Any massive intervention in Earth's natural systems carries risks of unexpected consequences. Our atmosphere isn't merely a repository for gaseous waste. It represents part of an intricately calibrated system affecting every breath and ecosystem interaction. Nevertheless, encouraging developments offer hope. Environmental quality has improved in numerous locations where regulations receive proper enforcement. America's Clean Air Act, for instance, has achieved dramatic reductions in key pollutants over recent decades. Europe, Japan, and portions of China have demonstrated similar progress. Even temporary lockdowns during the COVID-19 pandemic revealed how rapidly skies can clear when emissions decrease substantially. Monitoring sensors are becoming more affordable and widely distributed, enabling better tracking of environmental conditions. Community-driven science initiatives now empower individuals to monitor local environmental conditions while sharing real-time data globally. Satellite surveillance delivers comprehensive perspectives on contamination patterns across continents. These technological advances enhance transparency, inform policy decisions, and enable personal protection during hazardous periods. Shifting towards sustainable energy sources, minimizing fossil fuel dependence, electrifying transportation networks, and developing ecological infrastructure collectively contribute to cleaner atmospheric conditions. Vegetation plays crucial roles through particle filtration, oxygen generation, and temperature regulation. Metropolitan design, prioritizing pedestrian pathways, bicycle networks, and mass transit, reduces exhaust emissions while distributing benefits throughout neighborhoods. The challenge of compromised breathing environments extends beyond catastrophic scenarios to encompass gradual exposure, disparate vulnerability, and chronic health impacts. Most individuals won't experience days when oxygen completely disappears. However, countless people currently endure atmospheric conditions that gradually diminish their vitality. In this context, our planet's gaseous envelope transforms through changes both understated and profound. Our breathing medium encompasses far more than mere chemical composition. It represents environmental context itself. This invisible force transports pollen grains, fungal spores, bacterial organisms, and moisture content. It connects diverse ecosystems while moving seeds and biological signals. It provides cooling sensations, fills respiratory systems, and carries vocal communications. This medium serves as the foundation where all terrestrial existence unfolds. When this fundamental resource becomes compromised, consequences spread extensively beyond individual health to encompass entire ecological networks. Biological systems demonstrate remarkable persistence, discovering survival methods within boiling sulfurous springs, frozen wastelands, deep oceanic trenches, and radioactive contamination zones. Microscopic organisms endure acidic environments while algae inhabit solid rock formations. Various creatures enter dormant states lasting years. These exceptional life forms don't merely tolerate extreme circumstances, they flourish within them. Through studying these boundary cases, researchers gain valuable understanding about biological flexibility and limitations. The biosphere marred Earth's zone of living activity extends from deepest microbes embedded within oceanic crust to high-altitude bacteria suspended in upper atmospheric layers. Yet most complex organisms exist within much narrower bands, confined to specific elevation ranges and relatively restricted temperature, pressure, and chemical parameters. This habitable zone isn't permanently fixed, and species can shift within these boundaries. However, the edges reveal where survivability transitions into impossibility. Throughout the elevated Andes and Himalayan ranges, human populations inhabit locations where oxygen remains scarce and temperatures stay low. These communities develop distinctive physiological modifications, including enhanced lung capacity, elevated red blood cell concentrations, and modified metabolic processes. Nevertheless, definite ceilings exist beyond certain elevations. Human survival without assistance becomes impossible. Atmospheric density decreases, temperatures plummet, ultraviolet radiation intensifies. Eventually, even highly adapted physiology cannot function effectively. Deep oceanic environments support organisms surviving under tremendous pressure within complete darkness, utilizing chemosynthesis rather than photosynthesis near hydrothermal vents. Bacteria convert sulfur compounds into usable energy while tube worms, clams, and other creatures cluster around these thermal sources, forming isolated ecological communities. However, they depend entirely on vent heat and specific chemistry. When thermal vents cease activity, surrounding life gradually disappears. These represent highly specialized systems precisely calibrated to narrow environmental parameters. Desert regions challenge existence through extreme dryness. Certain microorganisms persist within Atacama desert soils where precipitation may not occur for years. They extract moisture from atmospheric humidity or generate metabolic water internally. Desert plants decelerate growth patterns, store water reserves, and shield tissues from solar radiation. Animals burrow underground, migrate seasonally, or modify behaviors to minimize heat exposure and water loss. Even here, absolute limits exist. Modern specific thresholds of aridity and temperature, biological activity surrenders to complete sterility. Polar territories add intense cold to survival challenges. Within Antarctica, simple organisms persist in ice-covered lakes, within rock crevices, or in seasonal melting zones. Algae bloom within sea ice formations while penguins and seals thrive along coastal areas. However, deeper into continental interiors where cold remains relentless and resources scarce, biological activity approaches zero. Ice transforms from ecosystem into mineral substance. These boundary zones matter tremendously because they demonstrate both biological capabilities and absolute restrictions. As Earth experiences warming, desiccation, and systemic shifts, certain regions may increasingly resemble these extreme environments. Coastal territories could experience flooding while inland areas overheat dramatically. Forest systems might transition into grasslands, then scrubland, eventually becoming dusty wastelands. The biosphere possesses mobility but only within limits. Species can adapt but only at certain speeds. Some organisms respond through migration patterns. Plant populations shift their ranges uphill or toward polar regions. Avian species alter traditional routes while fish modify spawning territories. Migration assumes accessible, suitable habitat exists. Within fragmented landscapes, this assumption often proves false. Transportation routes, urban development, and agricultural zones block movement corridors. Climatic zones may shift more rapidly than species can track them effectively. Others adapt within existing locations. Certain plants initiate earlier flowering cycles. Various insects adjust life cycle timing. Coral reef systems under stress might host more heat-tolerant algae varieties. Adaptation carries significant costs, though miners' energy devoted to stress tolerance cannot support growth or reproductive functions. Eventually, if pressure continues, population numbers decline substantially. Many species, particularly those with extended generation periods or highly specialized ecological niches, may fail to adapt entirely. Extinction represents the ultimate consequence of environmental pressure. While natural processes include species loss, current rates exceed background levels dramatically. Habitat destruction, contamination, climatic shifts, invasive species introduction, and resource overexploitation all contribute significantly. Conservative estimates suggest approximately 1 million species face extinction risks within coming decades. This includes not merely obscure insects or rare botanical specimens, but larger mammals, keystone species, and foundational systems supporting other organisms. Biodiversity encompasses more than numerical variety. It involves functional relationships. Diverse ecosystems typically demonstrate greater resilience, superior shock absorption capacity, enhanced recovery potential, and complex interaction support. When species vanish, these interconnections weaken substantially. Pollination services, seed dispersal mechanisms, soil formation processes, and water filtration systems all rely on intricate organismal networks. As these networks deteriorate, ecosystems become increasingly fragile. Microbial existence, forming the foundation of numerous systems, also shows sensitivity to environmental transformation. Within soil matrices, microbes cycle essential nutrients, decompose organic materials, and support plant root systems. Throughout oceanic environments, plankton establish food web foundations while helping regulate carbon cycles. Temperature, acidity, and chemical composition alterations can severely disrupt these critical roles. Ocean acidification driven by excessive carbon dioxide already affects shell-forming organisms including corals and mollusks. This disruption resonates throughout entire food chains. Researchers explore engineering resilience through assisted migration programs, selective breeding techniques, or genetic modification approaches. These tools remain controversial and uncertain. Numerous regions now witness renewable energy sources becoming the most economical option for fresh electricity generation. However, transforming the global energy infrastructure demands substantial time and coordinated efforts. This transformation encompasses not merely power generation, but storage capabilities, transmission networks, and regulatory frameworks. Solar installations function exclusively during daylight hours, while wind patterns remain inconsistent. Consequently, electrical grids must maintain flexibility through batteries, pumped storage facilities, and intelligent distribution systems that balance supply with demand fluctuations. These concepts aren't hypothetical future technologies. They're already operational across California, Germany, and various Chinese provinces. Transportation represents another critical sector requiring transformation. Automobiles, freight vehicles, maritime vessels, and aircraft consume fossil fuels extensively. Vehicle electrification, enhanced public transit systems, and urban redesign supporting pedestrian and cycling infrastructure collectively reduce emissions significantly. Aviation presents decarbonization challenges, though alternative fuel development and efficiency improvements show progress. Shipping industries can transition toward cleaner fuels while implementing smarter logistics systems. Every percentage reduction carries meaningful impact. Building infrastructure equally demands attention. Heating, cooling, illumination, and appliance systems consume substantial energy. Retrofitting existing structures for enhanced efficiency through superior insulation, efficient systems, and smart controls saves both financial resources and emissions. New construction can incorporate passive design principles utilizing sunlight, strategic shading, and natural airflow to maintain comfort with minimal energy requirements. Urban planning significantly influences these outcomes. Denser metropolitan areas featuring mixed-use zoning reduce travel necessities while supporting shared infrastructure systems. Industrial sectors, particularly cement, steel, and chemical production, generate substantial emission shares. Some processes prove difficult to replace since high temperatures and specific chemical reactions remain challenging to replicate without carbon involvement. Innovation progresses rapidly, though. Carbon capture technologies, alternative materials, and circular design principles all contribute solutions. Various manufacturing facilities experiment with hydrogen fuel, electric kilns, or carbon-negative production methods. Agricultural practices contribute through land utilization, methane emissions, and nitrous oxide release. Livestock operations, rice cultivation, and fertilizer applications all generate potent greenhouse gases. Reducing meat consumption, improving animal feed quality, managing waste products, and adopting regenerative farming practices can diminish environmental impact. Precision agriculture employs data analytics to apply water, nutrients, and treatments only where necessary, increasing operational efficiency. Redirecting subsidies towards sustainable practices aligns economic incentives appropriately. Forest systems, wetland areas, and soil matrices function as carbon absorption mechanisms. Protecting and restoring these natural systems helps extract atmospheric CO2. However, success involves more than simply planting trees. Diverse native ecosystems store greater carbon quantities while supporting enhanced biodiversity compared to monoculture plantations. Wetlands filter water supplies, buffer flood events, and capture methane emissions. Soil health influences both agricultural productivity and carbon storage capacity. Land management planning must consider not just vegetation coverage amounts, but vegetation types and strategic placement. Growing interest surrounds carbon removal technologies and strategies extracting CO2 directly from atmospheric sources. These include direct capture systems, bioenergy with carbon sequestration, enhanced weathering processes, and ocean fertilization techniques. Most remain in developmental stages requiring significant energy and material inputs. They cannot replace emission reduction efforts but offer potential supplementary solutions. Associated risks, costs, and scalability continue under investigation. Adaptation efforts demonstrate equal diversity. Coastal defense systems, including seawalls, dune restoration, and mangrove preservation, reduce flood risks. Early warning networks help communities prepare for storms, drought conditions, or heat wave events. Insurance models evolve to reflect emerging risk patterns. Building codes receive updates while infrastructure undergoes relocation or redesign. Some metropolitan areas restore natural buffer zones, allowing rivers to flood designated areas or reconnecting wetland systems to absorb runoff. Water management becomes increasingly important. Drought periods, flooding events, and altered precipitation patterns affect agricultural systems, drinking water supplies, and ecosystem health. Efficient irrigation methods, groundwater recharge programs, rainwater collection systems, and wastewater recycling help balance supply with demand. Certain regions require cross-border cooperation, since river systems flow through multiple nations and upstream decisions impact downstream users. Adaptation also encompasses social infrastructure. Healthcare services must address heat stress, disease pattern shifts, and mental health strain. Educational institutions can prepare students for emerging green employment opportunities. Emergency response systems must account for compound disasters, wildfires followed by floods, storms during pandemic conditions, supply chain disruptions. Equity remains central since vulnerable communities often face greatest risks while possessing few coping resources. Technology contributes significantly but doesn't provide universal solutions. Mobile applications can track environmental quality, provide fire warnings, or guide energy consumption. Sensor networks monitor crop conditions, power grids, and flood zones. Artificial intelligence assists in modeling climate risks and optimizing system performance. Without effective policy and inclusive governance, though, these tools may become distractions or exacerbate inequality. Implementation methods and beneficiary identification matter most. Financial mechanisms represent another influential factor. Investment decisions shape future outcomes. Banking institutions, insurance companies, and asset managers increasingly incorporate climate risk into decision-making processes. Various countries redirect subsidies away from fossil fuel industries. Green bonds, climate funds, and carbon pricing serve as tools aligning market forces with sustainability objectives. These mechanisms remain imperfect but signal shifting perspectives on risk assessment and value determination. Cultural transformation equally matters. Behavioral patterns, social norms, and consumer expectations influence consumption habits, mobility choices, and demand patterns. Dietary shifts, travel modifications, fashion trends, and housing preferences affect emission levels. These changes don't require individual perfection, but benefit from broad societal participation. Collective shifts supported by infrastructure development and policy frameworks make sustainable choices easier and more accessible. Hope doesn't assume automatic positive outcomes, or rather it involves finding purpose and agency when confronting difficulties. Realistic hope isn't naive. It acknowledges damage and risk while refusing to abandon possibility. This hope builds through action, not just large-scale innovation, but local initiatives. Community gardens, neighborhood cooling strategies, youth climate organizations, educators revising curricula, planners modifying zoning regulations, engineers redesigning electrical grids. Mitigation and adaptation cannot separate from justice principles. People bearing least responsibility for emissions often experience harshest consequences. Climate justice examines who benefits, who pays, and who makes decisions. It demands inclusion, fairness, and accountability. Just transition means not merely cleaner systems, but improved ones offering greater access, dignity, and resilience. Some change appears inevitable, yet much remains undetermined. The difference between 1.5 and 2 degrees of warming isn't theoretical. It affects crop productivity, storm severity, species survival rates, and human health outcomes. Every tenth of a degree carries significance. Every choice influences outcomes. When discussions about Earth becoming uninhabitable arise, conversations frequently shift towards space exploration. If our planet becomes excessively hot, arid, toxic, or stormy, could humanity simply relocate? Could we pack belongings, depart, and establish fresh beginnings on alternative worlds? This compelling concept has inspired science fiction for decades. Stories exploring interstellar travel, terraforming processes, space colonies, and new beginnings remain common, reflecting curiosity and underlying concerns about needing exit strategies. Transforming fictional concepts into reality involves extensive questions spanning physical, technical, ethical, and logistical considerations. Mars represents the most frequently mentioned candidate, relatively close by planetary standards, and most Earth-like within our solar system regarding day length and solid surface availability. However, describing Mars as Earth-like proves overly generous. The planet lacks any breathable atmospheric composition. Its gaseous envelope consists primarily of carbon dioxide. Surface pressure measures less than 1% of Earth's levels, meaning any human venturing outside without pressurized protective gear would lose consciousness within minutes. Temperature variations occur, yet average readings hover around -60 degrees Celsius. Liquid water remains rare, likely containing high salt concentrations or buried deep beneath surface layers. Radiation exposure presents another significant obstacle. Mars lacks Earth's protective magnetic field, leaving the surface continuously bombarded by cosmic radiation and solar particle streams. Our planet's atmospheric layers and magnetic shield deflect or absorb most dangerous radiation. On Mars, exposure accumulates rapidly, elevating cancer risks while degrading electronic equipment. Any human settlement would require extensive shielding through underground construction, thick protective barriers, or artificial magnetic field generation. Environmental challenges across Jupiter and Saturn's moons prove even more extreme without substantial infrastructure support. Any outposts established there would function as research installations rather than permanent residences. Consideration of departing our solar system entirely involves searching for exoplanets, Mars worlds orbiting distant stars, which has developed into a major astronomical field. Thousands have been identified, some within habitable zones where temperatures might permit liquid water existence. Even the nearest candidates lie light years away, though. Technology for transporting humans or rapid probes across such distances doesn't currently exist. Long-distance space travel physics involving time, energy requirements, and protection systems remain severely limiting factors. Terraforming concepts frequently enter these discussions. These involves transforming hostile planetary environments to resemble Earth more closely, warming Mars, thickening atmospheric density, releasing water reserves, eventually introducing plant life. Energy requirements and timescales prove massive, though. Terraforming demands planetary engineering surpassing anything humanity has accomplished. Even optimistic projections suggest centuries or millennia for completion, possibly remaining impossible given current physics understanding and available materials. Ethical considerations complicate matters further. Should we discover microbial or other life forms elsewhere? Do we possess rights to alter those worlds? Could we accidentally destroy ecosystems we barely comprehend? Space colonization conversations typically emphasize technical feasibility. Moral and ecological questions prove equally complex, though. Even if humans established settlements elsewhere, this wouldn't resolve Earth's problems. Population majorities would remain here. Space migration, should it occur, will be limited, expensive, and gradual. Earth continues housing billions. Should life-supporting systems break down, moist agriculture, water supplies, atmospheric conditions, climate stability, impacts arrive immediately. Space doesn't provide escape routes, but represents distant, challenging expansion possibilities. This doesn't diminish space exploration value. Satellites already support Earth systems through weather monitoring, emission tracking, disaster management, and communication services. Space-based solar power, asteroid mining, or orbital manufacturing could gradually shift industries off-world over extended periods. Telescopes, probes, and rovers expand understanding of planetary systems, including our own. Space exploration carries value, but Earth preservation remains essential. Worth noting, Earth already demonstrates incredible life-supporting design, not through intention but via billions of years of coevolutionary processes. Atmospheric composition, magnetic field protection, biodiversity richness, oceanic systems, weather patterns, and soil matrices collaborate within unmatched natural systems. Even ambitious space habitats would struggle replicating Earth's natural continuous functions. Efforts imagining life elsewhere, whether on Mars or orbital stations, frequently utilize Earth-based analogues for preparation. Research stations in Antarctica, underwater habitats, desert simulations, and International Space Station operations provide valuable insights. These environments teach isolation management, resource limitation handling, and closed system operations. They also demonstrate continued dependence on external support through resupply missions, communication links, and redundancy systems. Dreams of establishing second homes aren't misguided. They inspire exploration, innovation, and reflection. However, they cannot replace our current world. No discovered planet matches Earth's combination of habitability, accessibility, and evolutionary history. Despite current problems, Earth remains the most livable location we know. Rather than imagining fresh starts elsewhere, some redirect attention toward planetary repair possibilities, including ecological restoration, rewilding initiatives, reforestation projects, watershed rehabilitation. This encompasses economic shifts valuing sustainability and resilience, while recognizing this planet, despite flaws and pressures, retains more potential than any alternative. So regarding departure possibilities, yes, eventually perhaps with significant limitations. Better questions might ask whether we should treat this place as disposable or irreplaceable treasure. When people question Earth's potential uninhabitability, they typically mean uninhabitable for humans specifically. The planet doesn't require our presence for continuation. It needs no buildings, electricity, language, or cultural systems. Should humanity disappear gradually or suddenly, Earth would continue rotating. Sunrise would occur, precipitation would fall, tidal movements would persist. Organizational, maintenance, and interpretive changes would emerge. Over time, absence would register significantly. Imagining worlds without people has been explored previously through books, documentaries, and simulations mapping consequences of abandoned cities, decaying infrastructure, and ecosystems, reclaiming territories. Timelines vary, but patterns remain consistent. Within days, illumination would cease. Unmanaged power grids would fail as fuel depletes or solar installations deteriorate. Water treatment facilities would halt operations while plumbing systems experience backup failures. Buildings would deteriorate slowly initially, then accelerate as weather patterns, vegetation, and wildlife infiltrate structures. Within years, unchecked plant growth would emerge in parks, sidewalks, even high-rise buildings. Vines would climb upward, root systems would fracture foundations, grasses would proliferate extensively, warmer regions would witness rapid insect and small animal reclamation. Without traffic disturbances and noise pollution, larger mammals might venture into previously busy territories. Deer, coyotes, bears, wild canines would establish new territorial ranges. Where apex predators survive, mites, wolves, large felines, substantial birds' territorial boundaries would shift considerably. Domestic animals would face struggles. Some might survive and adapt successfully. Others, particularly breeds highly dependent on human care, would experience population declines. Pets trapped inside buildings wouldn't survive long periods. Farm animals might roam following fence deterioration, but many would encounter predation or starvation challenges. Urban adapted species, Nisir rats, pigeons, raccoons, might flourish initially before stabilizing as food sources diminish. Oceanic environments would witness shipping traffic disappearance. Underwater noise levels would decrease substantially. Fish populations could rebound in certain areas depending on contamination levels and habitat conditions. Coral reefs stressed by warming might continue bleaching and collapsing. Without additional pressures from trawling or tourism activities, though, recovery could prove possible in cooler regions. Coastal metropolitan areas would experience flooding over time, particularly those at or near sea level. Subway systems would fill with water while roadways would crack under plant root pressure and frost effects. Over decades, structural collapses would commence. Steel corrodes, concrete crumbles, glass fractures inevitably. Forest systems would expand into suburban territories. Agricultural land would revert to scrubland, subsequently developing into young forests if climatic conditions remain supportive. Species previously marginalized might return while others could disappear based on habitat damage extent already sustained. Over time, almost every artifact fades away. Without anyone to interpret those marks, any meaning gradually slips into obscurity. There's an irony in realizing that the very species capable of chronicling its own story might one day be absent, forgotten unless another consciousness emerges or arrives from elsewhere. In the absence of interpreters or storytellers, Earth's record returns to quiet, etched not in books or code, but in the layers of ice, sediment, and mineral beneath our feet. This isn't a gloomy vision, but a broader lens, a way to remember that the planet itself isn't brittle by cosmic standards. The true delicacy exists in the unique set of circumstances that make life familiar and interconnected. What's truly at stake isn't just the planet, it's the version of Earth that includes humanity, our communities, and all that we hold dear. It's not that a world without people loses all significance. It's simply that we are not fundamental to its cycles. Human presence fits within the broader frame of the system, but is not essential for its fundamental functions. That insight can provide clarity. It means that safeguarding Earth is less about abstract conservation and more about keeping our intricate networks and possibilities alive. Maintaining the suite of conditions that allow complex, vibrant life does more than preserve scenery. It nurtures us too. Earth's rotation, orbit around the Sun, its minor axial tilt and wobble, all continue whether anyone observes or intervenes, whether we build or abandon cities, whether climate discussions ignite or fade into silence. The mechanisms remain in motion, giving a subtle reassurance. Through stress and uncertainty, the environment persists. Sunlight warms the land. Gravity anchors the seas. Water travels the cycle from vapor to rain and back again. Seasons pass. Roots push through soil, creatures migrate. Even amid strain, many systems remain operational. Those ongoing rhythms provide the space for life to endure. Delicacy doesn't always signal weakness. A glass instrument can produce tones of immense precision, while a spider's web, fragile at a glance, weathers gusts and tension with ease. Hearth's feedback loops work similarly. Strength arises through movement, through interconnected responses, through balance. Yet, the composition of that balance is responsive. It shifts when pushed too forcefully or rapidly. For generations, we viewed the environment as mere backdrop, air as emptiness, dirt as inconvenience, oceans as endless. In time, we learn to recognize each as a responsive system, each sensitive to what enters and leaves. Unlimited extraction or careless dumping alters the parameters we depend on. Despite centuries of pressure, most of the world's essential functions persist. Fields yield harvests, waterways sustain flow, forests complete cycles of exchange. This reliability, while imperfect, deserves attention. It's common to approach environmental futures as binary choices, salvation or ruin, a single tipping point looming in the distance. Yet the reality is more gradual. Change accumulates over countless ordinary actions and small decisions. Warmer nights, marginally more acidic waves, a quietly vanishing species, a swelling flood. They rarely make headlines, but their collective influence builds tomorrow's foundation. Action arises within these gradual flows. New rules for construction, better farming tactics, incremental transport updates, lessons in classrooms, trees planted one at a time. Change most often resembles maintenance care, steady effort to lengthen sustainability. Well-designed infrastructure, clean energy sources, resilient ecological reserves are less about preventing every problem and more about stretching time, lowering stress, allowing circulation and renewal, subtle adaptation, shifts in food sourcing, safer laws for habitats, incremental energy reform. These matter, even if they're initially invisible to most. Much of the important work happens quietly, in policy revisions, in fieldwork, in data analysis, in school programs. Though lacking fanfare, these actions are indispensable. The paradox of vulnerability is that responsiveness remains possible. The phrase "it's not too late" echoes for good reason. Inputs still change outcomes. What is burned, protected, bought, or taught today will shape distant seasons in ways large and small. There is no all-or-nothing threshold. Certain processes may become fixed for a while, certain tipping points crossed, but the world's dynamism resists simple expiration dates. Environmental change emerges, unfolds, accelerates, or slows according to what we do. This can be daunting, but it is freeing as well. There's no single answer, no miracle intervention that resolves all. Instead, there are thousands of efforts, from villages to megacities, from individuals to international consortia. Progress isn't always visible, often falls short or feels unfair, but every action accumulates nonetheless. Knowledge grows, networks connect, tools improve, the baseline remains, even after all stress. Seeds lie dormant in soil, rainfall cycles persist, coral regenerate even on battered reefs. These realities call for action, not complacency. They urge us to safeguard what's left, to mend, rather than wait until absence becomes permanent. Permanence itself shifts meaning. Instead of aiming to fix the planet eternally, we turn toward continual stewardship. Environments require focus, not mere preservation. Infrastructure needs modification, not just maintenance. Cultures transform, technology evolves, values realign. The world we construct in coming years will differ from what has come before, but it can remain livable, meaningful, and rich with connection. This isn't nostalgia for a forgotten past or a desperate leap towards utopia. It's an invitation to encounter reality head-on, to understand the forces shaping us and reshape them in response. That involves science, but also values, emotional intelligence, collective memory. Watching Earth changes how we act. Understanding its chemistry, oceans, forests, and rhythms shifts decisions and directions. Awareness alone doesn't guarantee the right outcome, but it's indispensable as the first step. So the planet rotates, not untouched, not static, but not yet beyond our capacity to recognize and nurture. This moment holds multiple possibilities, with tools available and time remaining. It isn't unlimited, but it is still enough to matter, still enough to direct change. Across centuries, across coastlines, through countless questions, thank you for journeying through these ideas. Whether you stayed through, visited sporadically, or listened in passing, these thoughts continue gently with you. The aim was never to create alarm, but to illuminate what stays, what shifts, and what moves beneath us. Earth asks for nothing but offers everything: pattern, rhythm, and opening for continued care. Wherever you find yourself now, amid city streets, a quiet village, or somewhere in between, may certainty in the sky above, the ground below, and the evolving narrative around you bring comfort. Rest well, the unfolding story continues, waiting with you for the next sunrise.